Good afternoon, and welcome to the first webinar on EPA's Stormwater Pollution Prevention webinar series. EPA's Stormwater Pollution Prevention webinar series will highlight efforts to reduce pollution in stormwater through controlling pollutants at their source. Today's webinar will cover the topic of stormwater, coal tar seal coats, and polycyclic aromatic hydrocarbons, PAHs. The webinar will present information on the prevalence of PAHs from coal tar-based seal coats in the environment and on the environmental and human health impacts. The webinar will also cover actions taken to address PAHs by a state and a city. This webinar is sponsored by the EPA's Office of Wastewater Management Stormwater Program. I am Chris Montague-Breakwell, and I will be moderating the webinar. Thank you all for joining us today. We'll start by going over a few housekeeping items. The material in this and the views of the speakers and the speakers' organizations are their own and do not necessarily reflect those of the EPA. Mention of any commercial enterprise, product, or publication does not mean the EPA endorses them. First, I would like to briefly summarize some of the features of today's webinar. At this time, everyone is in listen-only mode. By default, all attendees enter using microphone and speakers. Please make sure that you have selected the correct audio settings in the GoToWebinar audio control panel, either telephone or microphone and speakers. We encourage you to submit questions to our speakers during this webinar. To ask a question, simply type it into the questions pane in the attendee control panel and click Send. If your control panel is not showing, simply click on the small orange box with the white arrow to expand it. Each speaker will give a half-hour presentation and take 10 minutes to question after the presentation. As the moderator, I will read the questions aloud so everyone can hear it, and the speaker will then answer. If you have any technical issues, you can let us know by entering it into the questions pane and then clicking on the Send button. We will do our best to respond to your issue by posting an answer in the questions box. This webinar will be recorded and archived so you can access it in a few weeks after today's live presentation. The archived webinar will be posted on EPA's NPDES training page at www.epa.gov/ntdes/training. It is now my pleasure to welcome and introduce our speakers. Our first speakers are Dr. Barbara Mahler and Dr. Peter Van Metre from the United States Geological Survey based in Austin, Texas. They will be presenting You're Standing on It, Coal Tar-Based Pavement Seal Coat, PAHs, and Environmental Contamination. Our second speaker will be Dr. Alison from the University of New Hampshire. She will be presenting PAHs and Parking Lots, a field study of PAHs exported from sealed and unsealed parking lots. Our third speaker will be Dr. Judy Crane from the Minnesota Pollution Control Agency, and her presentation will be Action in Minnesota to Address PAH-Contaminated Stormwater Pond Sediments by Restricting Usage of Coal Tar-Based Sealants. Our final presenter will be Mateo Scoggins from the city of Austin, Texas. His presentation will be the coal tar sealant ban and the science in Austin, Texas. One final note before we get started with our first speaker, we will try to answer as many questions as possible throughout this webinar. However, due to the high number of participants, not all questions will be answered. If you have any unanswered questions, please email the presenters directly. We will provide you with all of the presenters and EPA's contact information at the end of this webinar. Our first presentation is from Drs. Mahler and Van Metre from the United States Geological Service. Okay, Dr. Mahler and Van Metre, you can go ahead.
Okay, great. I think we're set up. Hopefully everyone can see our screen, and thank you for the introduction, Chris. We are, of course, very pleased that you've chosen the issue of coal tar-based seal coats and PAHs to kick off your new seminar series. And we're also very honored that you've asked us to participate as presenters in this webinar. This morning, or I guess this afternoon for some people out there and morning for others, we'd like to share the story with you of how we found that a widely used consumer product, one that's literally right under our noses that we're standing on, is a major and possibly the major source of urban PAHs in much of North America. Ph.D. Metre and I work for the U.S. Geological Survey, which is the largest federal earth science research organization. And the USGS researches more than just geology. Our mission areas include ecosystems and climate, hazards, human health, and, importantly for today, water. So Pete and I work for the National Water Quality Assessment Program, which is part of the USGS. That's what NAQUA stands for. And one of the main objectives of the NAQUA program is to understand trends in sediment and in water. In other words, is water quality and sediment quality, are they getting better or are they getting worse? And the way we go about this is to collect cores of sediment from lakes around the country. And we slice them up in little intervals and we analyze them for a suite of contaminants that tend to associate with sediment. And so we use these kind of like you would use tree rings to look back in time and see how contamination has changed over time in these lakes. Well, when we look at lakes across the country and we look at different contaminants, we see some different stories. We see some good news stories. On the graph I'm showing here, or the figure, each one of those symbols is a lake that we've cored. And we see for some contaminants like DDT and PCBs that most of the trends are downward. And so that's great to see that in the last 30 years, concentrations, as we move up the sediment to the most recent sediment, the concentrations are lower than they used to be. But a real eye-opener for us was to see that one group of contaminants, PAHs, are increasing in most of the urban lakes that we've sampled in the United States. So what's a PAH? Polycyclic aromatic hydrocarbon, which is a mouthful. PAHs are a large group of compounds that have as their backbone the benzene ring, which is the molecule I'm showing here. It's 6 carbons that are bonded into a ring, each of which has a little hydrogen ions or hydrogen atom sticking off of it. And if you think of the benzene ring like you would a 6-sided bathroom tile, you can arrange those in different numbers and different geometric configurations, and every one of those is a PAH. So as a consequence, there's a large number of PAHs, and they range from those with just a small number of benzene rings, like naphthalene, I'm showing here, 2 rings, that's the major ingredient in mini mothballs, all the way up to 3, 4, 5, 6, or even more benzene rings. Now, based on the number of rings and the configuration, these have different chemical properties, and that turns out to be important because those that are just a few rings, lower molecular weight, are more volatile, they're more soluble, and they're more toxic, but they're also more easily broken down. Those that have a large number of rings are less volatile and soluble. They tend to stick to sediment. They are more persistent. They stay around in the environment a lot longer, and they're more carcinogenic. So we're concerned about PAHs because many of them have been shown to be carcinogenic, meaning they cause cancer, teratogenic, meaning they cause birth defects, mutagenic, meaning they cause mutations, or toxic, meaning they kill things, to a range of species, and 7 PAHs are listed as probable human carcinogens. So there's a reason to be concerned for them in the environment, but they are ubiquitous in the urban environment because every time we burn organic matter, we create PAHs. Whether we are burning motor oil or gasoline or a hamburger or a cigarette, we're creating PAHs. And also those products that involve the combustion of organic matter, like tires or asphalt, also contain PAHs. So historically, it's been kind of a thorny job for environmental scientists to determine which PAHs are responsible for pollution because there are so many different sources. So that was our job when we saw these increasing trends in PAHs in urban lakes, was to figure out what's causing this increase. Let's take a look at a typical watershed, one that has undergone a lot of what we call new urban development. So this is for Lake in the Hills. It's a suburban community to the west of Chicago. And like many watersheds, in the 1970s, it was largely agricultural. There's a little bit of urban development right around the lake because it was a popular summertime place for popular summer houses if you lived in Chicago. And then as suburban development moved to the west, the watershed changed, and it now looks like many of the places where we work and live. There are single-family and multifamily residential housing. There is big box stores, there are shopping centers, there's churches, there's schools, there's roads, there's highways, and there are a lot of parking lots. And from our sediment core, what we see is as population in the watershed has increased, so have the concentrations of PAHs. So it looks like the PAHs are associated with people, but you know, people don't create PAHs. We're not excluding PAHs from our pores or breathing out PAHs. It has to be an activity that we're engaged in or a product that we're using that's causing these increase in PAHs. So the first clue to where some of these high concentrations of PAHs might be coming from came from the city of Austin. Back in the early 2000s, they had a grant from EPA, as a matter of fact, as part of their NPDES program. And they were using it to sample sediment in small drainages around the city. Now, we're not talking inner city or old industrial areas. These were drainages from largely residential areas, maybe some light commercial areas. They found very high concentrations of PAHs, greater than 1,000 milligrams per kilogram. And when they shared these data with us, at first we thought there was a problem with the lab, that maybe there was a decimal point in the wrong place, because we had not seen PAH concentrations this high in any of the urban lakes we've measured. And we've measured some lakes in some pretty nasty areas. So this really stood out. It's about 65 times higher than the probable effects concentration, where the PEC is the concentration above which we would expect to see negative effects on the benthic biota, the invertebrate critters that are living in the sediment. And so the question is, where are these high PAH concentrations coming from? And so what's upstream? And a very enterprising City of Austin staff member went upstream, and he saw parking lots. And the first question was, well, could it be the asphalt, the broken up asphalt in the parking lots that are contributing these high concentrations of PAHs? But it turns out that asphalt doesn't have very high concentrations of PAHs, and it couldn't be responsible for concentrations these high. But he also noticed that the parking lots had been treated or painted with a black product, and that black product is parking lot seal coat. Seal coat is a black liquid or emulsion that is sprayed or painted on asphalt pavement after the pavement's laid down. It's not part of the paving process. It's a product that a parking lot or driveway owner can choose to apply later on. It's typically applied to parking lots, to driveways, and even to playgrounds, but it's not applied typically to streets. So you'll notice in the lower left of your screen, you see a sharp contrast between the dark driveway there, which has the seal coat, and the light gray of the street, which does not have the seal coat. There are two principal types of seal coat. One has an asphalt or oil base, and one has a coal tar base. Now they look very similar, but they're chemically very different. Asphalt is, the asphalt oil base comes from the refining of petroleum products. The coal tar product contains coal tar pitch. So crude coal tar is the residue that remains from the coking of coal. The crude coal tar is taken and distilled, and during the distillation process, various lighter weight oils are removed. They have some commercial value. They're used in everything from pigments and paint to makeup. The residue that remains after that distillation process is coal tar pitch. Coal tar pitch is a known human carcinogen, and it's what goes into the coal tar seal coat product. And those products can contain anywhere from 20 to 35% or even a higher percentage of coal tar pitch. Now, when we first started looking into PAHs and seal coat, one thing that we heard anecdotally from folks in the industry was that the asphalt-based product was predominantly used west of the Continental Divide, and the coal tar-based product was predominantly used east of the Continental Divide. So in the Midwest, the northeastern United States, the southern U.S., it was predominantly the coal tar-based product. Now, our data backs that up, although that's not a hard and fast rule. There are some types of, each product is used to some degree in these two different geographic areas, but overall, the asphalt is more predominant in the west and the coal tar is more predominant in the east, largely for geographic and economic reasons. So let's take a look at PAH concentrations in some of the major urban sources of PAHs. These are values from the literature, and they range from very low concentrations, as I mentioned, from asphalt, well below 10, up to 440 for used motor oil, which has always been sort of pointed out as the bad boy of PAH contamination in urban environments. But if you took the sediment that the city of Austin collected from those urban drainages and you mixed it with used motor oil, you'd actually you'd clean up the sediment, because used motor oil has a lower concentration of PAHs than what was found in the sediment itself. The only way that you can come up with a concentration that high is to start with a source that's higher. So let's take a look at our seal coat products. Asphalt-based seal coat contains about 50 milligrams per kilogram, which is very similar to what's measured in tire particles. The coal tar-based product contains between 50,000 and 100,000 milligrams per kilogram. So right here you can imagine that even with quite a bit of dilution from dirt and sticks and leaves and whatever else ends up in sediment, the coal tar seal coat is still a very potent source of PAHs. So the concentrations are high, which is one of my criterion for environmental relevance of a contaminant source. And another one is the product or the contaminant source, is it used extensively? Well, seal coat use is indeed extensive. From the industry, we found that 85 million gallons of coal tar-based seal coat are used every year, and that's enough to cover about 170 square miles. If we look at individual watersheds, at those watersheds we've mapped in Austin, somewhere between 1% and 2% of the total watershed area is covered in seal-coated pavement. And that amount goes up if you go to different parts of the country. For example, in the Lake of the Hills watershed, that was the watershed for which I showed the core, 4% of that watershed area is covered in seal-coated pavement. About 40% of the parking lots are seal-coated, and almost 90% of the driveway area is seal-coated. And in that part of the country, it's the coal tar-based seal coat that is predominantly used. A third question for environmental relevance is, does the contaminant source stay where it's put, or does it get disseminated into the environment? Well, when we first apply seal coat, it makes a dark, shiny surface like shown on this driveway here. But after a few months, the abrasive action of car tires driving on the seal coat starts to wear the seal coat into fine particles, which can be removed by wind or by rain or by snow plows or even by sticking to vehicle tires and being carried off site. And eventually you start to see that gray underlying asphalt shown through as the seal coat is removed. And it's for this reason that seal coat applicators recommend that seal coat be reapplied anywhere from every 2 years to every 5 years. So it is being released into a range of different environmental compartments. If you go out and you just brush up some of the dust off a seal-coated parking lot, you'll see lots of little black bits, and those are the abraded bits of seal coat. So those abraded bits then are available to move off the parking lot, and they can move into a number of different compartments, some of which we've investigated. Let's start by taking a look at the pavement dust itself. So when we've gone to some of the urban lakes to collect sediment cores, while we were there, we also swept parking lots. It's a dirty job, but somebody's got to do it. And we swept parking lots in the same watersheds where the lakes were located, and we swept several. And what you're looking at here are median concentrations of PAHs in dust swept from seal-coated parking lots. And you'll notice that the concentrations in the eastern U.S. are about 1,000 times higher than those in the western U.S. Those in the eastern U.S. are very consistent with the concentrations that the city of Austin measured in some of those urban drainages, and they conform to what we've been told about these geographic differences in use. Now, we also swept parking lots that were unsealed in the same watersheds. We see a very different story. We still see low concentrations in the west, but we also see low concentrations in the east. Now, these parking lots are in the same watersheds. They're getting the same atmospheric deposition as the seal-coated parking lots. They're also getting vehicle exhaust and tire particles and leaking motor oil. The only difference between that top figure and the bottom figure is presence or absence of seal coat. Now, another thing you might notice is that the concentrations in the east on the unsealed pavement are a little bit higher than those in the west. And we think that what's causing that is off-site transport, that wind for adherence to car tires, you're even being pushed off by snowplows, that these particles are getting moved from sealed parking lots to unsealed parking lots. And some work done by Dr. Yanning Yang at the University of Illinois Champaign-Urbana corroborated this work very elegantly with a microscopic approach that found particles of coal tar pitch on unsealed parking lots. So let's move down a little bit now and look at runoff. So this pavement dust is mobile. It's available to be washed off parking lots with stormwater runoff. And one of the first studies we did was a little pilot study where we looked at particles in runoff from 13 parking lots in Austin, some of which were seal-coated and some of which were not seal-coated. So it's a pretty simple story. We're looking at a log y-axis here. What we find is that the concentrations of PAHs in the particles washing off the coal tar seal-coated parking lots is about 65 times greater than those washing off the unsealed parking lots. And they exceed the probable effects concentration by a factor of more than 100. Now, these concentrations are quite a bit higher than those we've measured even in the Charles River, which is in Boston Harbor, and that's one of the more contaminated sites we've ever measured. They're on the same scale as PAH concentrations at EPA Superfund sites that have been listed as Superfund because they're old manufactured gas plants or they're coal coking plants. They're plants where coal tar pitch was produced and there are very high concentrations of PAHs. And those are the concentrations that we're measuring in runoff from the parking lots. So let's move downstream a little bit. If it's in runoff, is it ending up in streams and lakes? And might these be contributing to the increasing concentrations of PAHs that we've measured in U.S. urban lakes? Well, to investigate this, we're going to use a method that's popularly called environmental forensics. And it stems from the fact that there is this wide variety of PAHs from low molecular weight to high molecular weight. And a PAH source has its own PAH fingerprint. It has a characteristic proportion of different PAHs. So for example, let's take a look here at the PAH fingerprint for the burning of coal. This is for coal emissions from coal-fired power plants. From left to right, we're looking at 3-ring PAHs up to the 5- and 6-ring PAHs. And each of those PAH is represented by a different proportion in the coal emissions, and that's its fingerprint. Now we're going to compare to that the PAH fingerprint for sediment from Lake Ann. Lake Ann is a lake in Reston, Virginia. It's a very lovely, high-end residential community, but the lake has high concentrations of PAHs. And we see for Lake Ann, there's some similarities and some differences to those coal emissions. And if we measure those statistically with the correlation coefficient, R, we get 0.6. Now, if R was 1, it would be a perfect match. And if R was 0, it would be no match at all. So we have something of a match. Maybe coal is contributing to those PAHs. Let's take a look at a different source. This is the PAH fingerprint for gasoline vehicle emissions. And if we compare that to Lake Ann, we see a slightly higher correlation coefficient, a slightly better match maybe gas vehicle emissions, exhaust emissions, are also potential source for PAHs to Lake Anne. Okay, so now let's look at the fingerprint for dust swept from coal tar seal coated parking lots. And this is data that we collected that I showed you a little bit earlier. If we compare that to Lake Anne, we see a very good match. And in fact, we see an R that is greater than 0.9. So this is strong, at least circumstantial evidence that dust from coal tar seal coated parking lots is contributing to the PAHs in Lake Anne. But we wanted to take a more rigorous approach. So we used a model that's been developed by the EPA called contaminant mass balance source apportionment. This is a statistical approach. And how it works is that it takes the PAH fingerprints for all the different PAH sources that you care to investigate, and it decides what combination of those sources, how much of each of those sources would you have to mix together to create the PAH fingerprint or profile in your sediment, or as they call it, your receptor. So in this case, the receptor is our lakes. It's our lake sediment. We used this approach and we tried out pretty much every PAH profile or fingerprint that we could find in the literature. And I divided them here into 5 different categories. We looked at used motor oil, we looked at tire wear, we looked at asphalt wear, we looked at exhaust in the vehicle category. We looked at different types of coal combustion emissions. We looked at wood emissions, and we looked also at a range of seal coat associated profiles, everything from the NIST standard for coal tar all the way down to the pavement dust off coal tar seal coated parking lots. So we did this for the most recent sediment deposited in 40 urban lakes that we've sampled, and I've divided these by the western U.S., the central U.S., and the eastern U.S. Each one of these bars is the PAH concentration in the sediment at the top of a core from an urban lake, and the height of the bar is the PAH concentration. The colors are associated with what the CMB mass balance approach told us was the contribution from a different source type. And what we see is that more than 50% of the PAHs are coming from coal tar-based seal coat. The other 2 major important contributors are vehicle exhaust and coal burning, which represent together somewhere between 30 and 40% of the contribution. We also see that for those lakes where the PAH concentration exceeds the PEC, the probable effect concentration, that in all but one case, that can be accounted for just by the contribution from coal tar-based seal coat. So let's circle back to our question about trends. Could coal tar-based seal coat be responsible for the upward trends that we've seen in lakes? Well, we looked at 6 of the lakes that we've sampled. These are new urban lakes, like the one in Lake of the Hills, where PAH concentrations are increasing. And we see that for 5 of these lakes, the increase is coming from the contribution from the coal tar-based seal coat, which are the orange symbols. The only one it's coming from something else, is in the lower left. That's Railroad Canyon Lake in Southern California, where coal tar-based seal coat is not very commonly used. And if you look at the y-axis for that lake, those are the PAH concentrations. PAH concentrations in this lake were about 100 times lower than in the other lakes. And in fact, this holds true. If we look at our lakes across the board, if we look at the 5 lakes that had low contribution from coal tar-based seal coat, the total PAH concentration is low. It's only about 3 milligrams per kilogram. So we can say that 3 is a baseline urban PAH concentration in the absence of coal tar-based seal coat. Those lakes that had a high contribution from coal tar-based seal coat also had high PAH concentrations, about 10 times higher on average, and those exceed the probable effect concentration, indicating that the coal tar seal coat may be contributing to deleterious effects on aquatic biota. Now, I'm not going to go into a great deal of detail about stormwater ponds because Drs. Watts and Crane are going to be giving you a lot more information about that. But I want to show you this because One of the hypotheses that was floated for these high concentrations of PAHs in urban lakes was atmospheric deposition. Well, if it's atmospheric deposition, we would expect two adjacent stormwater ponds to have similar PAH concentrations. But in fact, these ponds have very different PAH concentrations. The one to the south is about 45 times higher than the one to the north. What's the difference? Well, it can't be atmospheric deposition, but the one to the north is draining a parking lot that does not have seal coat, and the one to the south is draining a parking lot that does have seal coat. And in South Carolina, it is systematically coal tar-based seal coat that's used. So I mentioned the PEC. There has been a wide body of literature that's looked at effects of PAHs on aquatic biota. Since we identified the coal tar seal coat as a source, there have been some publications now in the peer-reviewed literature that are looking at the effects specifically of PAHs from coal tar seal coat on amphibians, on frogs and newts, and also on ecological communities. So that brings up the question of, well, what about human health? I'm not going to go into a great deal of detail here because we're focusing on stormwater. But we have done studies that have looked at PAHs in house dust and in air, which are two logical pathways for human exposure. What we found was that house dust in residences that were adjacent to parking lots with coal tar-based seal coat, the pH concentrations were 25 times, not 25%, but 25 times higher than pH concentrations in house dust in residences that were adjacent to unsealed asphalt or asphalt with the asphalt-based seal coat products for the parking lot. The air story, if you're interested in air quality, this is pretty interesting. We've recently started looking at volatilization, and just after seal coat is applied, many of the lower molecular weight PAHs in particular are quite volatile, and you smell it. This stuff is volatilizing into the air at a very large rate. In fact, over the first couple of weeks, about half of the PAHs are lost just to the air. And if we compare what comes off a newly seal-coated parking lot with a coal tar-based seal coat to an unsealed asphalt parking lot, tens of thousands of times higher concentrations and fluxes are going into the air. If you do a mass balance and you compare the amount of PAHs going into the air each year from newly seal-coated parking lots, that's with coal tar-based seal coat, it exceeds the PAHs being produced by vehicle emissions across the United States. So to sum up, coal tar-based seal coat satisfies three criterion for environmental relevance. The concentrations are extremely high, the use is extensive, and it's transported off-site. And it's transported to pretty much every environmental compartment we've looked at, whether it's lake sediment or soil, house dust or air. PAH concentrations are tens to thousands of times those in background. And there are associated potential effects for aquatic biota and also for human health. We do have a website that has information. You can get links to our publications. I think we have about 10 publications now in the peer-reviewed literature, and we have 5 USGS publications, including a real nice short fact sheet that sums all of this up. It has some FAQs. It has links to other sources of information. And I've also put my email address. As Chris mentioned, you are more than welcome to contact me or Dr. Van Metre if you have any questions about this subject. And I think I've just about used my 30 minutes. And Chris, at this point, are we going to address questions?
Yes, we'll do questions. We only have a few so far, so we'll start. First question, does seal coat actually provide any protection to asphalt, or is it merely cosmetic? And has marketing turned disposal of a waste product into a social norm?
Well, I have to say right up front that Pete and I are environmental scientists. We are not pavement engineers. We have requested information on how effective seal coat is at preventing deterioration of the underlying asphalt. and we have not been able to find any either ourselves in the literature, nor have we been provided any from the industry. I'm sure that they're doing tests to try and determine that, but we're not able to find any information to answer that question one way or the other. The second question is sort of a social cultural question that is one that somebody who's an expert in marketing might be able to answer far better than we can.
Okay, thank you. Next question, are there differences between seal coats that are applied to streets and highways and seal coats applied to parking lots and driveways?
Yeah, this is Pete. They're, in general, the ones applied to streets, especially the stuff that they call chip sealing, is a different product. That's most likely an oil-based or asphalt-based product. This kind of seal coat, the thin coating that doesn't have the rock chips in there, is almost exclusively used on parking lots and driveways. The one exception that I've seen was a process called fog sealing that is, I think, a thinner, maybe more dilute, pavement rejuvenating kind of product that I gather is used on roadways and that can be made from coal tar base. But I have very little idea of how extensive that use is. I just found one mention of it on the web from Utah, but as far as how much of that is done, I don't know.
Okay, thank you, Pete. Next question is, are there alternative seal coats available with less pH concentrations, and are these being explored?
Well, the asphalt-based seal coat has far lower concentrations, on the order of what you would find in tire particles, so around 50. But there are polymer seal coats that I believe have even lower pH concentrations, and that's something that Mateo Scoggins is going to address in his presentation a little bit later this afternoon.
As far as availability, the asphalt, as far as we know, the asphalt sealants are available pretty much nationwide.
They're harder to get in some places than others.
Yeah, but especially in the retail store, the 5-gallon bucket you can buy at the home improvement store. In fact, in many cases, that is the major retail chains have switched to the asphalt products for homeowner use.
Okay. Thank you. Next question, is the seal coat used for parking lots different from tar used from roofing houses?
No, actually it's very similar, and I believe that the same geographic differences exist for whether it's a coal tar-based product or an asphalt-based product. From an environmental standpoint, this is going to sound flippant, and it's not, but I don't mean it to be. We don't drive on roofs. So the real issue for releasing the PAHs into stormwater is the fact that the tires are abrading it. So in areas where there's no tire traffic, the PAH doesn't, the seal coat doesn't wear very rapidly, and so there's a much lower yield of PAHs off the surface that's not being driven on. It's the abrasive action of the tires that's wearing the seal coat and breaking it up into the small particles that then are washed off.
There is another issue, though, that we haven't done a study of yet. That having done the recent studies the last couple of years on volatilization rates off of freshly seal-coated pavement and seeing that they're just extremely high, I don't see any reason that a similar product applied on a rooftop wouldn't also be volatilizing at a very high rate.
Okay, thank you. Next question. Quote, I was wondering if there are any best practices for disposing of coal tar debris from remediated sites. Unquote.
Again, that's one that as environmental scientists, as research hydrologists, that's not an aspect of this that we've addressed, but that's a question that I think Mateo is going to be able to address in his presentation, because the City of Austin has confronted that very question.
Okay. Next question, what would the cost of roadways being what they are? If these products improved life cycle cost, then every city and DOT in the country would be using them. So it seems that they do not increase life cycle benefit. I guess that's more a statement than question. But do you guys have anything to say regarding that?
In a sense, that's a similar question to the first one. So they're not used on roads because they wear off the road surface too fast from the heavy traffic. But they are used on parking lots. So I guess the question goes back to the first one. You know, what is the life cycle benefit to a parking lot? Certainly, if you're concerned about PAH releases to the environment, even if you make the asphalt last twice as long, where at half the rate, the PAH release from the asphalt is trivial compared to from the seal coat. So there's really no benefit there. But as far as the cost-benefit analysis of the pavement itself, that's a question we haven't addressed and aren't trained to address.
Thank you, Pete. Next question is, this might be another question for pavement engineers, but I'm curious about parking lots that have been designed to drain away water or reduce runoff. Can seal coats be used on those surfaces, or would it render them non-porous? And actually, our office does a lot of green infrastructure work, and no, you would definitely not want to apply that to a permeable asphalt or a porous paver or something like that. That would seal it and prevent the entire purpose of it draining down and actually infiltrating. Pete, if you want to speak a bit more about that, go right ahead.
I think you gave a fine answer, Chris.
Let's see. I'm scrolling through the many questions we're getting. Have you? Sorry here. Quote, how are you able to conclude from the source of PAHs, conclude that the source of PAHs were from coal-based pavement seal coats that are from other sources such as coal plants, gas stations, etc.? You went over PAH fingerprints. Is there one for coal-based pavement seal coat?
I'm not sure I fully understand, but I mean separating out coal-based pavement seal coat signal from other coal tar related sources like old industrial sites. Is that what they're getting at?
Yeah,
the question asked separating it from coal plants or gas stations.
Well, many of the lakes that we've sampled and the parking lots that we've sampled are in areas where there are no coal gasification or
yeah, so a lot of it is just sort of proximity and common sense. So if you're sampling in a suburban area that was once cornfields and is far removed from industrial sites, and you see this very rapid recent increase in PAHs that coincide with urbanization, then you know it's not from 100 years ago, some coal plant in Chicago. Lake in the Hills is a real nice example of that. So when we did that whole modeling study, the sources, one of the things we did do is identify all of the active coking plants in the U.S. and then figured out how close to those any of our lakes were. And very few of the lakes were within even 100 miles of a coking plant, and most of them are further than that, different parts of the country. So proximity is and just, to some extent, common sense comes into the source analysis.
It's similar to what we saw with the stormwater ponds, where two adjacent stormwater ponds have very different concentrations of PAHs. So even if there is an atmospheric source, coal, even if there were a coal processing plant 10 miles away, it would be affecting both of those stormwater ponds similarly.
Now there are sites in older urban industrial areas in the Ohio River Valley or up in the northeastern U.S. that do have coal gas plants and do have legacy contamination from those. We've only looked a little bit just out of curiosity, since we don't tend to core in those kind of sites. But we have looked at the chemical profile from soils from coal gas plant waste sites, and it's largely very similar to the profile from coal tar-based seal coat, because it's pretty much the same stuff. So, if you are looking at sediments from one of those, downstream of one of those sites, I think it's a much trickier job to see if you could separate the two.
Okay. Thank you so much, Drs. Van Mahler and Metre. We're now going to switch to Dr. Alison Watts from the University of New Hampshire. But before we switch, I'd like to say for the people who came on late and have been asking questions, this presentation and the individual slideshows will be posted online at the EPA site in just a few weeks, and you will receive an email after this webinar with a link to that, as well as the final wrap-up slide will show you the web link to that. And without further ado, I'm going to switch to Dr. Watts from the University of New Hampshire.
Hello?
Hi, we can hear you.
You can hear me. Okay. I'd like to thank Chris very much for inviting me to speak at this. I really appreciate the opportunity, and I thank all, it was 450 something that I looked at last time, of you who have logged in to view this webinar. Is my screen up?
It is not. You need to accept that I've given you presenter powers. There should be a little box saying, there you go. You're on.
I'm on. Okay, excellent. I want to spend a little bit of time talking about a study that we've done at the University of New Hampshire. This study was actually born to some extent after I had seen some of the initial data that came from the City of Austin and from USGS in 2005 and 2006, and some of that Dr. Mahler has already discussed. And a lot of the samples that they've taken show very convincing evidence that coal tar sealant is a source of PAHs. But those samples are taken in the real world, and the real world is a very complicated place. And as Dr. Mahler discussed, PAHs are ubiquitous. They come from a lot of different sources. Any sample that you take out in the environment is likely to contain PAHs at some level or another. And it's often very difficult to distinguish how much a particular source is contributing to pH concentrations in a given sample. And I thought that it would be really helpful in the processes of discussion around this issue to look closely at a controlled site where we have sealant applied in some areas and no sealant applied in other areas, and we do extensive sampling and determine what the difference in PAHs are under those semi-controlled conditions. So we did a study out at the University of New Hampshire Stormwater site. We are the staff of the Stormwater Center. University of New Hampshire is in Durham, New Hampshire. We're a fairly rural area, just a little bit north of Boston. The Stormwater field site is a testing facility which is designed to test a variety of different kinds of stormwater treatments. So what we have is we have a 9-acre parking lot a little bit north of the university. The area inside that blue line is about 9 acres, and everything that the rain that falls on that surface all drains off into the corner to that north side, which is where our test center is. The really perfect thing about the site for this type of study is that there are actually 2 separate areas. There's one up in the north near our test facility and one over here on the side. And those areas actually drain separately from the main site. So we can sample the stormwater from those 2 little areas separately from the main flow. And so we felt that this study could be implemented at the site very easily. We had a sealant contractor come in and apply coal tar-based sealant to those 2 separate areas. We asked them to just sort of apply it in a normal way as they would at any commercial site or any university parking lot. Not that the university actually does use sealant, but if they had been. So we had sealant applied in these 2 areas, and then that whole center section, which is about 9 acres, has no sealant applied at all. And I just think, in response to the question about porous pavement, if you see lot V down there on the side, the section next to it that is not sealed is actually porous pavement. That's a test lot for porous pavement. And our center director was very, very nervous that we would accidentally get some of that sealant over into the porous pavement, because I think it would have really destroyed the pavement. So we have these 2 areas. We had that sealant applied in October of 2007. And the question that we really wanted to address is, where does the sealant go? You have it put down, it's applied, it's this beautiful black shiny surface. You come back a couple of years later and most of that sealant is gone. And that's what's expected. It's not intended to last. It's intended to last for a couple of years, and then the manufacturers expect you to reapply it. So it's not intended to be a permanent treatment, but if it's gone, what we really wanted to study was where does it go and what pathways does it travel down. And that's a picture of that B lot right after the sealant is applied, and then about a year later. You can see that some of the color is starting to go, and the white lines, we had it restriped after the sealant was applied, so the paint is also starting to wear off. So what are the primary mechanisms for moving sealant? Dr. Mahler discussed this a bit. Primarily abrasion from tires and from driving over the surface. Plowing has a significant impact on the surface, tracking on tires. There's a little bit of weathering from either the heat or solar radiation on the surface. And then those particulates are carried away by stormwater or by wind. We didn't look at volatilization much in this study, but some of the recent research that USGS has done suggests that volatilization is also a significant method of moving PAHs off the surface. Here in New England, the plow is a significant, moves a significant amount of the seal coat. If you look at the surface of a parking lot in New England in the spring, you can see the scars and gashes where the plow has gone over it. If you look at the snowbanks that have been moved, you can see the little particulates of sealant. And in the spring, after the snow has melted, we see a fine layer of sealant particulates where those snowbanks were. So we sampled several different pathways. We looked at stormwater runoff. We sampled about 24 storms. We aim to do about 1 storm a month. It depends, of course, a bit on the weather and what's available. We also sampled sediments in a swale that receives stormwater runoff and in a couple of different stormwater devices. We sampled surface soil adjacent to the site at both the sealed and the unsealed areas. And then we sampled pavement dust, which was swept off the surface. All of these samples were analyzed for the 16 priority PAHs, and then a subset were analyzed for an extended suite, which included some of the homologs and some of the more complicated PAH compounds. So the sampling was done by automated ISCO samplers for the stormwater. For those of you who are experienced at sampling stormwater, you don't want to go out there in the pouring rain and do it yourself with buckets. It's a lot easier to do if you have these automated samplers. They're set to respond as soon as the flow starts off the site, and the volume is set by the length of storm and the volume that's coming off in the stormwater runoff. We had 3 samplers at the head of the site. One of these is sampling runoff from the unsealed control. One is sampling from a lot, and then one is a duplicate sampler that's taking duplicate samples. We collected both physical water samples. So this is the inside of one of those samplers. All those are little sample bottles. The samples are collected in Teflon bags and then sent out to a lab for analysis. We also collect real-time data on water quality. So we have a probe that sits in the flow that collects flow, temperature, pH, dissolved oxygen, and a bunch of other things. And those probes are on all the time, so we have a continuous record of flow and water quality at the site. Some of the samples that we collected were discrete samplers, which is what you see in that picture there with the different bottles, and every certain amount of time a new bottle is collected. Some of the samples that we took, in fact most of the samples that we took, were actually volume-weighted samples. So we have an average that represents the real average concentration over the course of the storm. So for instance, here's the results from one of the storms that we sampled. You can see the blue line is the flow coming off the site. It starts to rain at about 9 o'clock in the morning. The flow increases, goes up and down. And then the red triangles represent the concentration of PAHs in micrograms per liter. And as you can see, they're higher at the beginning of the storm and then decrease in concentration over the course of the storm. And this is common in stormwater samples. This is what we normally see. It's referred to as a first flush phenomenon. When you have a parking lot surface, you have debris, you have dust on that surface, a lot of that initial wash-off comes off in the first sort of flow from the storm. And then as the storm goes on, the water becomes cleaner and cleaner. So if you're ever looking at stormwater sampling results, be quite careful if you're looking at what we call grab samples, which is where you just go in and you take one sample during the course of the storm, because that may well not be representative of the concentrations that are collected over the entire course of the storm. So we started sampling almost immediately after the sealant was laid down. We had our first rainstorm about 24 hours later. And these are the first samples that we collected. And I was quite startled. I didn't really expect to see that coming off one of my parking lots. The sample from Lot A is not actually a dark fluid. What that is a clear fluid with a very fine suspension of little black particles, so little tiny bits of seal coats suspended in the stormwater. We saw that in the first flush coming off of this parking lot. We never saw it again. That was just some initial wash-off that started at the beginning of the storm. When we looked at the parking lots after the storm was completed, we didn't see any evidence of loss of seal coat. Both of the parking lots looked the same. We didn't see any residual in any of the stormwater devices that receive flow from this. So we think that this happened in that initial wash-off. What we don't know is how often you get these high concentrations after a sealant is applied. The sealant was applied as according to the manufacturer's directions. As I said, we had a contractor who came in to do that. We asked them to do what they normally do. It was a warm, sunny day. It rained about 24 hours after the second coat was applied. So let's look at the results of the stormwater sampling. These are the samples that were collected over our 2-year sampling period. On the left, you can see that we have the total pH concentration in micrograms per liter, and that's a log scale, so there's a very significant difference in concentration. The red squares and diamonds are the concentrations that came off the 2 seal blocks. The blue circles are concentrations coming off that unsealed control in the center. And you can see that the concentrations coming off both of the sealed blocks are higher for all of these storms that we sampled. They're much higher right at the beginning. In the first quarter, we saw much higher concentrations, and then they gradually seem to be decreasing. If we had continued sampling, my guess is that we would eventually see all of this merging to about the same concentration. It's important to point out, I think, that there are definitely PAHs coming off that unsealed control. So even though there's no sealant there, we do have PAHs in stormwater, and we see that in a lot of different areas. Stormwater is a known source of PAHs to a lot of receiving bodies. Then we wanted to get a handle on what was the mass of PAHs coming off the parking lots in these different media. So what's the mass of PAHs being exported from the parking lots in stormwater? We took the concentrations that we measured, we did a mean for each quarter, and then we took the total volume of runoff that we've measured at each of those sampling stations, and we developed an estimated mass per quarter for each of the parking lots. And what you can see is that the mass coming off each of the parking lots is actually roughly the same, and that's in spite of the difference in sizes. So because the unsealed control is so much larger, even though the concentrations are lower, the total mass coming off. But if you normalize that per acre, if you look at just the amount of mass coming off each acre of surface over this 2-year period, the total mass coming off the unsealed control lot is about 0.13 kilograms, where the total mass coming off the other 2 sealed lots is more on the order of 4 kilograms. So we have significantly greater mass coming off of the 2 sealed lots. And remember again that these lots are adjacent, so there's atmospheric deposition, there's whatever history there is related to this parking lot, but those outside factors are the same. The only thing that's really different is the application of the seal coat. We also looked at concentrations in surface soil. So again, this is a sort of a schematic of the site. The dots represent total pH concentrations in the very top layer of soil. Yellow is fairly low concentrations, less than 10 milligrams per kilogram. The orange is pretty much in between, and the red is the higher concentration. And you can see that there are definitely higher concentrations clustered around the areas that have been seal coated. The circles are soil, and the stars are dust sweeping samples. So the stars are dust off the surface. And in places where we went back and sampled again, you can see there's a line and there's two different colors. And sometimes the sampling, the return sampling or the duplicate sampling, had fairly different results, and that's kind of life in soil sampling. There's variation within a very small area. So the concentrations are much higher around the sealed lot. If you look over towards B lot, the one down on the side of the main parking lot where the porous pavement was, if you remember that, you can see that there are some high concentrations down there next to the unsealed surface, and that's directly related to the plowing pattern. The plow comes through over that sealed surface, and then because of the way the bushes and some of the sampling equipment we have, they pile the snow up next to that unsealed surface. And that's clearly transported some of the seal coat material off into that section of the parking lot. And the highest concentrations that we saw were a little over 400 milligrams per kilogram. Benzoate pyrene there at 29.2 milligrams per kilogram. Those are quite high concentrations. This is a university parking lot. People aren't hanging around there a lot. But if this were a residential parking lot and children were playing on that surface or playing in that soil, I think that we would probably be worried about some of those health effects. We also tried to do an estimate of the mass of PAHs transported off the parking lots into soil. So we just took those concentrations, we did a little bit of averaging over the area, and we estimated that there was on the order of 1 kilogram to 1.5 kilograms of PAHs associated with each of these parking lots in the soil. I think that that's probably a significant underestimation because we didn't actually sample very far from the site. There's probably elevated concentrations at a greater distance, but as we merge into the background, it becomes more and more difficult to tell whether we're looking at concentrations in the background or elevated concentrations from the site. And then just for comparison, we also did some sampling at a couple of other university parking lots. So these are parking lots in the same town, but not in the same parking lot, sort of in the same study area directly. And again, we saw relatively low concentrations in the dust and in the adjacent soil. These are pretty equivalent to background PAH concentrations in this area. We've done a fair amount of sampling for other projects, and we rarely see PAHs over about 5, maybe at the highest 10 milligrams per kilogram in surface soil. And we also spent a fair amount of time looking at concentrations in stormwater sediments. And I think that Dr. Crane is going to talk more about stormwater later, but we did this very direct study looking at the concentrations related to our site. So this is a picture of our stormwater site, the test site. The various sort of depressions in the ground that you see there are different treatment systems. There's a gravel wetland, the kind of green thing is a stormwater pond. There's various other pieces there. Flow from the main site comes on to these different treatment systems, comes down the side in a swale. And so there you go. The main site, the 9 acres, moves down the swale on the side and mixes with flow from the smaller coal tar steel site. So the flow that comes down onto the site is mixed from both of these parking lots. We went out and we sampled sediments before the sealant was applied, and the numbers in black at the top, sort of as these columns of numbers, are the samples that were collected prior to any kind of sealant. So you can see the concentration, the highest concentration there is a little bit over 3 milligrams per kilogram. And this is a swale that's been in existence probably for, I think, 3 or 4 years at this point. So it's certainly not a pristine environment. It's been receiving stormwater. It has collected some PAHs either from atmospheric deposition or from that stormwater, and it has this background layer. The water comes down through the swale, through a little stormwater pond, and then eventually discharges into a little wetland over there in the corner. So we also did some sampling in the wetland to sort of try and get a handle on how far the PAHs were transported down from the site. Then we sampled again 9 months after the sealant was applied, and you can see that the concentrations are much higher. So more on the order of 90, 50 milligrams per kilogram in the swale, starting to be elevated in some of those downstream locations as well. And we continue to sample a year, and then at the end, 3 years after the sealant was applied, we still see elevated concentrations, even 3 years after the sealant is applied. And I am only looking at surface sediments here, so these are fairly fresh sediments which have been probably deposited within that 3-year period. We also looked at, and just for reference, if you look at the 9-acre parking lot and the relative sizes of the sealed and the unsealed areas, this represents a watershed in which approximately 4% of the surface is seal coated. And if you remember Dr. Mahler's presentation, she was representing some of those watersheds. I think the Lake of the Clouds had on the order of 4% of the watershed seal coated. So this is representative of the amount of seal coat that we might see in a fairly common suburban neighborhood. We also looked at concentrations in several of the other stormwater devices. Up there at the top of the slide, you can see the concentrations in, we sampled a gravel wetland, a bioretention, and a detention pond. Each of those stormwater devices has a little area at the opening into the treatment system where sediments collect. We just called it a sediment forebay. So we collected surface sediments from those forebays, and we collected the sediments over the course of the study. So some of them were fairly shortly after the seal coat were applied, and the most recent ones were late last summer, so approximately 4 years after sealant was applied. And we still see elevated concentrations 4 years after the sealant was applied. We have approximately 100 to 160 milligrams per kilogram, in the devices which are receiving stormwater from the mixed sealed and unsealed surface. And then over in this one little area on the side where we had all of the flow from that parking lot goes into a small tree filter. We sampled the sediments in that tree filter from an area with 100% sealed surface. And we had concentrations up to 1,700 milligrams per kilogram. When we went back and sampled that last summer, those were still extremely high. I think it was about 600. So again, we're still seeing those elevated concentrations quite a long time after the sealant's applied. Somewhere in the middle of the study, for other reasons, we put a small bioretention system in the median, right in the middle of the parking lot, and that's collecting stormwater from about 1/4 of an acre adjacent to the cars there. We also sampled that, and we sampled it several times, and the concentrations are consistently below 2 milligrams per kilogram. So again, the outside PAH inputs at the site are exactly the same in that little bioretention and, for instance, the tree filter. The only difference is the application of seal coat. So just in summary, we see a very clear correlation between increase in seal coat and concentration in the stormwater sediments. So the conclusions are pretty much that there is definitely an impact from the coal tar-based seal coat on pH concentrations in each of these media. In stormwater, we saw an increase on the order of magnitude over the course of the first 2 years. Concentrations do decrease with time. And then the surface soil, we saw concentrations up to about 400 milligrams per kilogram. And we don't really have a time series on that, but assumably those concentrations would also decrease with time. The stormwater sediments, we have concentrations that significantly increase with the amount of sealed surface, so up to 1,000 milligrams per kilogram in areas where the entire parking lot has been sealed, and we still see those elevated concentrations 4 years after application. We have a little handout pamphlet that Sea Grant put together for us. If anyone's interested in it, that is on our website. and I'll take questions. I can't resist this slide because people have a tendency to say that seal coat is only applied during warm and sunny weather, and this was several years ago. I was skiing with my kids in March, and we drove home, and someone had just finished seal coating their driveway, so you never know what people are going to do. All right, are there questions?
Okay, now we'll open the floor to questions. Our first question is, in your study you tested 24 hours after the seal coat was applied. Is there a typical curing time for seal coat?
That particular manufacturer recommended 7 hours. And so, yes, the applicators do have specific curing times, and that applicator was 7 hours.
Okay, thank you. Next question. How is monitoring for total PAHs done? Is there a total of individual pH compounds? And if so, how were mirror non-detects handled for the low concentration samples? Yes,
it's a sum. In most of these analyses, we simply did not include the non-detects. When we're doing the SIMS, the SIM analysis, is extremely low detection limits. So we just did not use the non-detects.
Next question. What DMPs can be used to reduce PAHs in runoff?
Well, the good news about all those PAHs in the stormwater devices is that they're doing their job. So the fact that the PAHs are in the stormwater sediments means that they are not in the runoff. We did a little bit of sampling of stormwater that had run through the systems, and they were all extremely low. So we saw almost no PAHs that were not removed by treatment. And I didn't show it, but we also did a little bit of work looking at how much of the pH concentration is bound to sediments, as in if you filter the sample, do you remove most of the PAHs? And the answer is that most of it is bound to particulates. So if you have a stormwater treatment device that removes the particulates, you're going to do a really good job on the PAHs. On the other hand, then they're in the stormwater treatment device, so you still got them.
Okay. Our next question is twofer. The first part is how bioavailable are PAHs and how toxic, and the second question, which I think can be answered with the same answer, is what type of impacts might we look at in water bodies to demonstrate that water quality or aquatic life impacts are occurring?
Yeah, I am not going to go deeply into that. I'm not a biologist. All I can do is compare it directly to screening levels, and what we do see are concentrations that exceed screening levels. The question of bioavailability and pH is ongoing, and I don't think I can really address it.
Do you have any future research topics from UNH on this topic?
We don't, at this moment, we don't have any additional projects. The piece that we do have a piece starting to look at some of the forensic data, the statistical data that Dr. Mahler was looking at, and trying to see if we can determine the difference between coal tar from manufactured gas plants, of which we have a lot around here, and whether we can actually distinguish that from coal tar from parking lots. And I have to say that so far I'd say that we can't. There are some slight differences, but they're pretty subtle.
Okay, thank you so much. We're going to end questions now and go to our next presenter. Thank you, Dr. Watts. Our next presenter is Dr. Judy Crane from the Minnesota Pollution Control Agency in St. Paul, Minnesota.
Thanks so much, Chris. I really appreciate you inviting me today, and I think this webinar is such a great resource for folks. I'm just looking at things here, trying to get my presentation to come up. Do you see it?
Yes.
Okay. We'll get started here. All right. Today I'm going to talk about what we're doing in Minnesota related to contaminated stormwater ponds, which are getting contaminated with PAHs, and then also some efforts to restrict the usage of coal tar-based sealants, which, as you've heard from our previous presentations, are a major source of pHs in many urban environments. Now, a lot of people, or Minnesota is known by a lot of folks as the land of 10,000 lakes. Well, we have over twice that amount of stormwater ponds just in the Twin Cities area. Oops. And I couldn't get my slides. Oh, there we go. Sorry. To give you an overview of what I'll be talking about today, I'll be going through why we're concerned about pHs building up in our stormwater pond sediments here in Minnesota, how different units of government in Minnesota are addressing this issue, what the most likely sources of pHs are to these stormwater ponds, and then I'll just tell you right off the bat that the coal tar-based sealants are the major source of pHs, so what are we doing about that? In Minnesota, we're finding that the stormwater ponds are filling up with sediment. And this isn't surprising because they're going to fill up with sediment over time. But Minnesota has been a leader in using stormwater ponds as a best management practice for treating stormwater to have the flow water get reduced in the stormwater ponds so the suspended sediments settle out, and also as a flood control mechanism. So about 30 years ago, when these stormwater ponds were really starting to be put in a lot of suburbs around the Twin Cities area of Minneapolis, St. Paul, at that time, most people were more concerned about maybe metals building up in the sediments. Nobody really thought about pHs. And so our agency at the Minnesota Pollution Control Agency, we require stormwater ponds that are permitted by us to be analyzed for pHs and a couple of metals before the municipalities do any maintenance dredging to remove those sediments. And there are some states, I might add, around the country that they have no requirements for any analysis of sediments before they're dredged out of stormwater ponds. So I would be interested in hearing from some other folks at the end of this presentation from other states on what kind of requirements they have for stormwater ponds to be analyzed for contaminants. So the issue is that as these ponds fill up, they're not functioning properly, and municipalities must then have them dredged out. And this removal of pH contaminated sediments, especially at higher contaminated levels, can be quite expensive, and it's put a big chill on a lot of municipalities in being able to deal with this issue. In White Bear Lake, Minnesota, received cost estimates of $250,000 just to clean out 2 stormwater ponds in 2007. And a lot of cities, they don't have the money to do these type of cleanups. You know, some municipalities have hundreds of these stormwater ponds that they're responsible for. So in the most contaminated sediments, it really hampers the options that municipalities have to use that dredge material and to dispose of it. And the cities have requested a solution from the Minnesota legislature and also the MPCA. So Don Berger, in our stormwater program, he estimated the cost per disposal. And in Minnesota, we have, depending on the level of contamination of pHs, the sediments can kind of fall into 3 different levels. And the level 3 dredge material is the most contaminated. And so the sediment must either be disposed of in a specially lined landfill, like it could be used for clean cover on a landfill, or other approved options. We have a situation now with one municipality that they've received approval to have the dredge material from their pond be encapsulated in a berm that's going to be built up around the pond. So the disposal costs vary with landfill, and Don looked at a couple of landfills around here, and he came up with a total cost estimate of about $40 to $50 per cubic yard. However, if the material has to be treated as a waste instead of cover material, it's going to be even more expensive to dispose of that material. And Don estimated that if just 10% of the estimated 20,000 stormwater ponds in the Twin Cities area here were in that level 3 judged material classification, it could cost $1 billion to dispose of that material. So this is a really big emerging problem here in Minnesota. And I think it's one that a lot of other states are going to be dealing with as their stormwater ponds that were maybe implemented later than ours start to fill up and they have to deal with them. So as we've heard in the previous presentations, coal tar-based sealants have really emerged as an important source of pHs, and in our case to stormwater ponds, but to other urban water bodies as well. And so this is an issue that we've been tracking here at the MPCA since the USGS started publishing their work in the peer-reviewed literature. I used to be on an emerging issues team at the MPCA, and we listed the coal tar-based sealants as one of our important emerging issues in our 2007 emerging issues inventory. So I've been providing some technical assistance to our stormwater program for about probably 3.5 years now, especially on this issue of the pH contamination in the ponds. And I spearheaded the production of this pH white paper that's available on our website. As Chris mentioned, all of the presentations will be available on the EPA's website in a few weeks, so don't bother having to write down the web link there. You can access that later. But this gives a good summary of the issues that we're facing and a literature survey of the research to date when this paper came out in 2010. And as we've heard previously, asphalt-based sealants are a suitable alternative to the coal tar-based sealants. It's really a simple solution that people can use asphalt-based sealants or acrylic-type sealants that have no pHs, or there's even like gilsonite sealants that don't have pHs. And about a year ago, I did a survey of several home improvement stores and hardware stores, and some other staff at our agency have done some additional work on that. And so there are a number of retailers that no longer sell the 5-gallon buckets of the coal tar-based sealants that homeowners could purchase and put on their driveway. They do usually sell the asphalt base, and a lot of times they will sell the acrylic-based sealants too. The acrylic sealants are a lot more expensive than the asphalt-based sealants. So the legislature has also been very responsive to this issue. In 2009, they provided us with funding to study this issue. They directed us to do a number of tasks, of which are detailed on our website link that I give there. An example of a few is that we didn't really know how many stormwater ponds are actually in the permit program that our agency deals with municipalities. So there's an inventory of stormwater ponds. That's one component of it. Don Berger of our staff worked with the League of Minnesota Cities to draft a model ordinance that cities could consider using if they wanted to ban coal tar-based sealants in their municipalities. The legislature also banned state agencies from purchasing undiluted coal tar-based sealant in 2010. So there was a really great carrot that the legislature put in there for municipalities. So they had language in there that if the municipalities would pass an ordinance prohibiting or restricting the use of coal tar-based sealants, that they could be considered for a grant that our agency would give out to treat contaminated sediments in their stormwater ponds. And as a result, there's 20 municipalities in Minnesota have passed ordinances. As you'll hear in Mateo's talk after mine, Austin, Texas was the first city to pass an ordinance prohibiting the use of coal tar-based sealants, followed by Dane County, Wisconsin, and Washington, D.C., and then there's been Washington State has passed a statewide ban, and other places have passed restrictions. So it's great that we have 20 municipalities now that have passed ordinances. These municipalities don't actually have to tell us that they have passed an ordinance, so I oftentimes find out through a Google search or Tom Ennis, with his Coal Tar Free America blog site, he oftentimes knows before we do. So he now has a section on his website where you can plot where the different bands are, which is where this information came from. Now, another component of the legislative funding was to fund a stormwater pond sediment study. And there's a little bit of serendipity here. Back in 2008, I was assisting our stormwater program with putting together a proposal to do a study of stormwater pond sediments, and that was submitted to a special legislative group. Well, it didn't get funded, but Representative Scoggins, that was on the committee looking at the proposals, thought it was a good proposal, it should be funded, and that's really what led to this legislative action, that it provided the money to fund that study that I had wanted to do, and also she provided these extra tasks for the agency to do and the additional incentive there for municipalities to pass bans. So with this study that I was in charge of doing, we limited it to stormwater ponds that were in the municipal separate storm sewer system, or the MS4. And also they were limited to stormwater ponds in the 7-county Minneapolis-St. Paul metropolitan area here that I'm showing on the map, as those would be representative of other MS4s around the state. So we kind of had a short duration to get the study underway. The project was funded. The money came in July 1st, and we were out in October doing the sampling. And to get this project done, really got a lot of great input from municipalities around the Twin Cities area. We tapped into their expertise to get them to recommend ponds to us that were either in major residential, commercial, or industrial land use type areas. So the actual ponds we ended up sampling are shown on this map. And we did the sampling during October, and we were kind of like the mail carriers of the sampling world. We were out there in nice sunny weather to begin with, but then October quickly deteriorated to being one of the coldest and wettest Octobers on record. So it got snowed on twice, and then by the time Minnesota Public Radio came out to do a story on us, it was like hypothermia weather and very cold, rainy weather. But we persevered, and because a lot of these stormwater ponds have a lot of vegetation around them, cattails and such, because they want to keep people out of them, they're a little bit harder to get into. And some of these stormwater ponds are very small, some are larger. So we use field kayaks to do our sampling. And we sampled 3 sites across each pond. And we use a modified drop core here to collect the upper 15 centimeters of sediment. And the sediment actually went into a very clean Pyrex mixing bowl that's in that blue bucket there. And it would take several samples collected at each site to get enough mass and material. And then that was ferried back to land where I processed the samples. So we had 3 different sites that were sampled, and then we had some extra sediment set aside from each one of those samples that was composited together. So we had our 3 samples and we had our composite sample. And there were a large number of chemicals analyzed on these sediment samples. I'll just talk today about the pH analyses, but we did have 4 different groups of emerging contaminants analyzed on these samples, in part because we wanted to see, are there emerging contaminants in these samples that we're going to be concerned about too. So we wanted to be very thorough in the type of work that we were doing. But with the pHs, we had 2 different types of pHs analyzed. We had parent and carcinogenic pHs analyzed by a local laboratory that we have a state contract with. And then we had, and the carcinogenic pHs were especially important for our calculations of benzoate pyrene equivalents that I'll talk about. And then also we had parent and alkylated pHs that were analyzed on just the composite samples. And those were analyzed by Mateo. And so those parent and alkylated pHs were very important and were used for environmental forensic work. And as Barbara talked about this morning, the pHs have a fingerprint that can be used to determine sources of those pHs in environmental samples. So the results. Well, based on a sum of 13 pHs, and these are, each one of these pH compounds are ones that we have sediment quality targets for the protection of benthic organisms. And these are basically, we adopted the consensus-based sediment quality guidelines that you've heard about some by Barbara, the probable effect concentrations, and which are the higher bound value, and then also the lower threshold effect concentration. But we call them our level 1 and level 2 sediment quality targets. And on this map, we see each of our sampling sites, whether they were in a residential, commercial, or industrial area, and then the concentration values. The blue is less than our level 1 sediment quality target. Yellow is between the level 1 and level 2, and the red is greater than the level 2 sediment quality target. So we have 2 industrial sites and a commercial site that were all greater than the level 2 sediment quality target. And these sites also exceeded the equilibrium partitioning sediment benchmark toxic units of 1. So that would indicate that detrimental impacts to benthic critters and the sediments at those sites would be probably happening. Now this site in Bloomington was interesting. This had the highest pH concentrations. The total pH concentrations were about 130 milligrams per kilogram dry weight. And this site happened to be right by an area where the city of Bloomington processes their street sweepings. So they're getting all the goo and stuff that is building up in the street, and they sweep it off with these big machines in the spring and then deposit it there, and some of that was obviously running off into this pond. And then also up here in New Brighton, where the pH contamination was high, this was a former brownfield site. And then this commercial area in North St. Paul was a site that had both commercial and residential input into it. And it was actually just a very small stormwater pond, but it had a lot of pavement around it as well. And then also the pH contamination in the industrial sites were statistically greater than in the residential sites. So, okay, well, let's move on then to calculating the benzoate pyrene equivalent. So these were calculated based on the carcinogenic pHs that were measured using our potency equivalency factors. And the values, the VAP equivalents, were compared to our soil reference values of 2 is soil reference value of 2 is for a residential site, and 3 is our level 2 soil reference value. And depending on how the values fall, we get our different categories of our dredge material. So what's really a major concern is when you get into the level 3 dredge material. And 60% of our ponds, 9 of the ponds, were at that level. So this would be the most expensive disposal that a municipality would have to do. You know, if we get back to that case where White Bear Lake got an estimate of $250,000 just to clean out 2 stormwater ponds with the sediments in it. So that's a lot of money. Now, you might note here that there are 4 ponds that had non-detect data, and this was really surprising. pHs are such a ubiquitous class of contaminants. I wasn't expecting, you know, non-detect data for all of the pHs for those sites. So I wanted to find out what happened. And in closer evaluation of the procedures the lab used, the analytical lab was a production lab, and they used, well, instead of, let me back up, a lot of these sediment samples from these stormwater ponds, they're pretty gunky, not to use a scientific term, but they're really a lot of goo and stuff in them, and it's very hard for the analytical work to get all that gunk separated out. So it's a lot of what we call our interferences. And in these samples, the interferences were quite high. And so this lab, what it would do to try to remove those interferences is it would dilute the sample extract, sometimes several times. And what that ended up doing is it increased the reporting limits. So it ended up increasing the reporting limits so much that for some of these ponds, all the data came back as non-detects. So the other lab that we use, we got much better data, and they use cleanup columns. So one thing that we are recommending to municipalities when they have their pH analyses done is to talk to the labs and make sure that they're using cleanup columns instead of diluting the sample extract. Okay, so moving on, let me just go back just a second here. Another thing about these calculations is that our agency and the Minnesota Department of Health are in the process of evaluating new toxicity data that's available or is in draft form from the EPA, and it's likely that at some point this year we will be changing the procedures for how the benzoate pyrene equivalents are calculated, and then also how the soil reference values are calculated. So it could end up, increasing or decreasing these cutoff values. All right, so Barbara talked some about using environmental forensic techniques. We're not going to solve any murders here, but we are going to help to solve a mystery. So where are these pHs coming from? Well, there's some general categories that you can divvy your sample results up into just based on what type of pHs you find. And so we know that pyrroline, for example, is a diagenic or a natural pH, and that some other pHs, especially some of the alkylated ones, are more oil-based. They're what we call petrogenic pHs. And then there's a lot of pHs that are what we call pyrogenic. They come from combustion-type sources. So in our samples, we're seeing that most of the pHs are falling into this pyrogenic category, and the diagenic are very, very low, as we would expect. There was one pond in particular that kind of broke the mold from the other ponds, and it was called Lavender Pond. It was actually a natural little pond or lake that had stormwater diverted to it, so it became a stormwater pond, and that's pretty common around here. Minnesota has a lot of lakes, and so some municipalities have taken lakes or wetlands and then kind of converted them for stormwater pond use. And with that particular pond, Lavender Pond, it was in a residential area, and it had low concentrations of pHs, so the pyrroline that was in there, the natural pH, made up a greater proportion of those pHs, so that's why we see it's at 12% in that pond. And then also it was located by a major road, so the oil-based pHs were higher in that sample. But with most of the other samples, they were pretty consistent with the range of pHs that they displayed. And so I'm going to show you next the results of this EPA CMV model that I used that Barbara did a really nice overview of that model. And that model, the end result of it, the sources that came out of it, really fell more into this pyrogenic fraction. So, this summary here is nice to kind of get general classifications, but it doesn't tell you how much might be from coal tar-based sealants versus power plant emissions or from the combustion of coal or diesel. So that's what I'll go through next. And then at the end of my presentation, I'll kind of put this all together with taking the diagenic source, the petrogenic source, and then breaking this pyrogenic source into a lot of different sources that we can find out from using the CMV model, and then putting that all together into a pie chart to kind of bring it all home. So the quantitative techniques, like Barbara mentioned, they provide a nice, rigorous method for apportioning sources. You know, some people also use statistical techniques like principal components analysis to try to determine where the data separates and to try to determine sources. But one thing with principal components analysis is that it's very data intensive. And so you really should have at least 50 samples to use principal components analysis, and it's even better if you have hundreds of samples. And one thing that I like about the CMV model is that you could really just use it for a couple of samples. So it's really nice if a municipality wanted to use it, for example, that they or their consultants could be trained to use it and that they could get an idea of the assemblage of pHs they have in their ponds. So Barbara talked some about how the model works. So, and I want to thank Pete Van Metre and Barbara Mahler for being so generous with their time. They've really helped me out to learn this model. They have shared their source profiles with me, and you know, I don't know if I could have done that. I couldn't have done this work as well as I have without their input. So I really appreciate their assistance. So this model helps to figures out the best combination of sources to match your sediment sample. And with this particular case, with the study that I did, it worked extremely well. And the two major sources that came out as being important in these stormwater pond sediments were coal tar-based sealants and traffic tunnel air. And so we can think of traffic tunnel air as like if you went into a highway tunnel and you had some air measuring device there, you could measure all the emissions that were coming off of the vehicles going through that tunnel. That's what that represents. So it's a mobile source of pHs. And when the coal tar-based sealant sum, what that is, it's a sum of coal tar dust profiles and then also coal tar sealant scrapings data that the USGS has obtained, or as you heard Barbara talk earlier in her presentation with how they did the studies to obtain that data. Now the model includes 12 of the 34 pHs, and it would be great if we could use a greater number of pHs in the model, but that is kind of a limiting factor of some of the other source profiles that are available, that they only have 12 pHs. And really, if you got into using a lot more pHs, you probably get into a lot more non-detect issues with some of the data, would have non-detect for some of those, so then how do you treat that? So there'd be different issues with that. Now the statistical results of this model I was extremely happy with. The R-squared, ideally you'd want it to be 1, and it's 0.98, so it was quite high. It was very good. The chi-squared values were low. The percent mass, ideally it would be 100%, and here it came out to 100.6. The t-value is another statistical measure that if it's less than 2, it can be an indication that you have collinearity between your sources. And here it was greater than 2, which is what we would want to see for 10 of the ponds for coal tar sealant scraping. So that's really indicating this is a really important, distinct source. And the mean relative percent difference between what we measured in the sediment samples for these 12 pHs and calculated based on the model was less than 1%. So that's incredibly good. So I feel very confident in these results. Now, I also ran this model on a different data set, and this was a data set that the Metropolitan Council collected on behalf of the MPCA for a study that we gave them the funding to do. And they looked at different stormwater ponds around the Twin Cities area. They had 10 different ponds, and they sampled 5 sites in each pond. However, this was the first and only time they had done the parent and alkylated pHs. So there were some data quality issues with some of their data. So I did a a QA/QC review of their data and determined that I could use 26 of the 50 sediment samples they had. And then also with their study, they looked at a variable depth interval of their samples, and they didn't actually record what that depth interval was for each site. So, you know, we know they were between 15 and 45 centimeters. And with that study, it also came out very close to mine that the coal tar-based sealant sum was the major source. But then they also saw other sources like the wood combustion or coal, the traffic tunnel air, also being sources. And that might be because you have that you have a history that's developed in that sediment profile. And so if they had a longer sediment core, then maybe there were other sources that were more prevalent back at that time, with whatever time interval that sediment corresponded to. The statistical results of the model were acceptable with their data. It wasn't as great as my study, but it was still quite good. And so then to summarize here, the coal tar-based sealants were the biggest source of pHs to stormwater ponds, and then also lake sediments in the Twin Cities, because Ph.D. Metre and Barbara Mahler, they have also sampled a couple of lakes here in the Twin Cities. They sampled the west lobe of Palmer Lake and in a suburb of the Twin Cities, and that mean concentration was 72.2%. And I believe their use of the model, they only used the coal tar sealant dust, so they didn't use both the dust and the scrapings. I use both the dust and the scrapings because here in Minnesota, we oftentimes get a lot of snow in the wintertime, and so there's a lot of snowplow action, shoveling, snowblower action that's helping to abrade the sealant even more. And then Lake Harriet, which is in Minneapolis and is in an older neighborhood, that have a lower percentage of coal tar-based sealants. So this model really provided a better estimate of combustion sources, as I mentioned earlier. So what I'm going to do now is just to apportion the results of what I have with the model and multiply it by the pyrogenic fraction of the pHs at 82.6% that I showed in an earlier slide. So here's the pie chart I promised. So it comes out that the coal tar-based sealants comprise about 58% of the total pHs. The oil-based petrogenic sources are 15%. This traffic tunnel air is also about 15%. And then lower percentages of other sources like coal combustion, diesel combustion, the natural sources, pine wood combustion, oil burner, and gasoline combustion. So there are some other efforts by the PCA to reduce the usage of coal tar-based sealants. And Al Innes at our agency brought in a Great Lakes Restoration Initiative grant from the EPA to promote the phase-out of coal tar-based sealants. And the MPCA is taking the lead on this, and he's working with folks from Michigan and Wisconsin on it. They just started the grant last fall, and they have several tasks. One was to try to implement a voluntary phase-out of coal tar-based sealants in Minnesota in partnership with the Pavement Coating Technology Council. This partnership could not be negotiated, so we've moved on with other activities, and another was to contact retailers to build on that survey that I had done a year ago to determine where it's still being sold and try to promote voluntary phase-outs. I determined that Sears is still selling coal tar-based sealants, and I think they have been trying to contact Sears management to see if they can get them to phase out the use of it. A real big success story here is that Jet Black, which is a commercial applicator, has committed to switch from coal tar-based sealants to asphalt-based sealants in Minnesota and Wisconsin over the next 2 years. And they're also promoting this use in 10 other states. So they are the largest commercial applicator in the U.S. And 2 days ago, they got an award from our governors via our MPCA commissioner for their pollution prevention efforts. Al and his group are also going to work with other users to try to phase out coal tar-based sealants and work with suppliers and researchers to try to promote feasible alternatives that hopefully have no pHs in them. And then importantly, he and his collaborators will be sharing these strategies and products with other states. It's a very important component of the project. So if you want further information about anything with the scientific technical issues, like with the stormwater pond study I've conducted, you can contact me. Any policy management issues, you can contact Marnie Karnowski, the supervisor of the municipal stormwater unit. Any of the pollution prevention issues associated with this GLRI grant, you can contact Al. And then also we have a web page on the culture-based sealants and restricting their use. Thanks so much. So I'll take any questions.
Okay, thank you. First question, what does proper disposal of pH contaminated sediments entail?
Right. Well, if the dredge material is in the level 3 category, that material can either be used as a clean cover at a specially lined landfill, or if the landfill determines that if it's determined to be hazardous waste, then it would have to actually be disposed of in the landfill. Now, this is a problem because, you know, there's limited landfill space too to dispose of all this material.
Next question. You mentioned retailers that no longer sell coal tar-based sealants. Is this just in Minnesota or nationwide?
No, this is pretty much nationwide, yeah. It's been known for several years that Lowe's and Home Depot quit selling coal tar-based sealants as a result of the ban that was passed in Austin, Texas. And I also contacted them to follow up on that. Excuse me. And then, like I did a variety of Google searches and looked at the MSDS sheets for products, coal tar sealant or asphalt-based sealant products that manufacturers put out. And for example, Agway is a retailer that's just located in the Northeast U.S., so I determined that they don't use the coal tar-based sealants anymore, whereas Menards is one that's located more in the upper Midwest, and so they don't use it either.
Next question. What types of ordinances have cities in Minnesota implemented, bans or restrictions, for instance?
Right. A number of them have used the model ordinance language that Don Berger developed in consultation with the League of Minnesota Cities. So sometimes the language of that was to ban the use of undiluted coal tar, because that's kind of how it was phrased in the legislative language. But some municipalities in their ordinances, they may have a fine of several $100s or $1,000 that would be imposed if somebody's caught using the coal tar-based sealants. And then other ordinances don't mention any fine, so they just say that they don't want to have it used in their municipality anymore. And then some of them also provide a stipulation that if somebody is doing a research project, that then they would be allowed to use it. So there's different language with the ordinances. If one wants to do a Google search of Minnesota or city ordinances, coal tar-based sealants, then a lot of these ordinances will pop up and they can look at them themselves.
Next question. Just a clarification question. When you were discussing the lab errors and testing for PAHs, did you say to make sure that the lab uses, quote, cleanup column, unquote? If so, what are cleanup columns?
Right, good question. Yeah, it wasn't a lab error so much as a procedure that labs use. A lot of these high production labs that may have offered lower costs for their analysis, they kind of get are able to achieve that, and sometimes by using cost-saving measures like diluting the sample extract instead of running it through a cleanup column. And so a cleanup column is something that may have alumina. It's like it actually is a glass column. It may have different components. It can have alumina or silica gel in it. And so, like when you're doing the analytical process, you tried to extract the pHs off of the sediment sample. You have this liquid solvent sample that the pHs are in, and then you can actually run that sample extract through this column, and it'll percolate down through the column, and so some of these interfering compounds will be removed by the alumina or silica gel, and sometimes they put a little layer of copper in there too to remove sulfides. And then what comes out of the bottom is cleaner, and then that can be reduced down and then inserted onto the GC mass spec type system to get your actual concentration data for the pHs.
Next question. Does it follow that if the MPCA calculation of 10% level 3 ponds yielded a $1 billion cleanup estimate, then the 60% study level would yield a potential cleanup cost of $6 billion?
No. And the reason for that, I was thinking about this earlier, the reason for that is that we don't know yet, really, how many ponds are in residential areas versus commercial versus industrial. So in my study, we had 5 ponds in each category. But maybe in the Twin Cities or all of the MS4s in Minnesota, maybe you have more of a mix, like maybe it's 60% residential, maybe it's 20% commercial and 20% industrial. So it was more, the industrial ponds were statistically significant higher concentrations of pHs, and those were the ones, well actually quite a few of the ponds, yeah, quite a few of the ponds ended up in that level 3 material. But still, I think we would have to have a better accounting of how many ponds are actually in each type of land use classification. And then the other issue that comes up is that how these benzoate pyrene equivalents are calculated, and then also how the soil reference values are determined is likely going to be changing later on this fall based on new toxicity data that's become available. So I can't really say whether they're going to go up or down. I mean, I kind of myself have my own feeling for what's going to happen. I think it's going to be more helpful to municipalities, but at this point can't say. So they can stay tuned, and probably by this fall we'll have some new information out on how those will be calculated.
Next question is, did your sampling include private homeowner ponds, or were they just municipal ponds?
Right, that's a good question too. Yeah, I mentioned near the beginning of my field study that we just limited to the regulated ponds in the MS4 program. It would have been nice to have included some private ponds too, especially, but then again, you know, you have to get them to volunteer a pond, and it was a little challenging with this study to get enough ponds in the industrial category. And there were some ponds that I went to that, for example, they had too much cattail detritus in the sediments, and we couldn't get a cohesive sediment sample, so then we couldn't use those ponds. So there was kind of like one last-ditch email I sent out to the municipalities to try to get another industrial pond that I could look at that we did end up including in the study. So no, there were no private ponds included in the study.
Next question. Why did Minnesota ban coal tar sealant products for government agencies but not for private use? And how can cities deal with its private use?
Right. When that legislation was passed, actually the legislature almost had put in a statewide ban on coal tar-based sealants. But at the time, I think it was the League of Minnesota Cities wanted to have more information collected on how it might impact businesses to have a statewide ban. So, so they initiated the ban on just state agencies, and really that was more for show because the Department of Transportation in Minnesota, for example, hasn't used coal tar-based sealants for years. And I don't think any other state agencies were really using it anyway. But it's in there in the language. And then the second question was what with how city, could you repeat that one?
How can cities deal with the private use of the coal tar-based sealant?
Is that if they, well, if they pass their own ordinance, then they have that they can use for enforcing it. And then some municipalities, actually quite a few municipalities have quarterly newsletters that go out to their citizens, or they have it on their website. And so a number of them have been putting information in these newsletters to encourage people to quit using coal tar-based sealants and to switch to asphalt or not even use any sealant at all. And really, I mean, people have many alternatives to them. They can have different types of driveways. They could have concrete, permeable pavers, you know, gravel. You know, you don't have to have an asphalt driveway. And also, since a lot of retailers aren't carrying the coal tar-based sealant anymore, except for like Sears, and I think that's maybe the major one around here in Minnesota where you can even find it. You know, there's not as many places where a private owner could get that material.
Okay, we have no further questions at this time. Thank you, Dr. Crane, for speaking.
Yeah, thanks so much.
We now move to our final speaker, Mateo Scoggins from the city of Austin, Texas. And Mateo, I'm going to hand over presentation powers to you.
Okay, everybody, can you hear me?
Can you speak up a little, Mateo?
Yeah.
We just lost his audio. Okay, I'm going to chat him. Chat message. We've lost speaker power for the moment. I'm going to try and get Mateo back on. Stand by.
Chris, this is Judy. Could I mention one other thing?
Go ahead, Judy, while we try and get Mateo on the line.
Just while we're trying to get Mateo on, is that also there has been federal legislation that has been proposed, and I think it's in some committee right now to try to have a nationwide ban on coal tar-based sealants. Now, it probably doesn't have much of a chance of getting passed, but at least there has been some activity by the federal government in that regard.
Okay. Thank you, Judy. We're still waiting for Mateo Scoggins to call back in. We can see his screen, but he's locked audio.
Oh, it's me. I'm back.
Back.
Sorry about that. My phone got disconnected.
Okay. Glad to have you back. Go right ahead.
Okay. All right. Let me know if is that you seeing the full screen there?
Yes, it's up and running. Go right ahead.
Okay. Thanks everybody for hanging in there. Again, my name is Mateo Scoggins. I work for the city of Austin. And I'm really going to be giving you a kind of an overview of a lot of stuff that folks have talked about today because we've been involved with this story since the very beginning. But I'm going to try to graze over some of the chronology of it because Barbara Mahler did a great job of kind of overviewing how this whole story developed. And I'm going to be focusing on a couple things. One is really what our focus was, which is we kind of learned very quickly in this process in about 2003 or 4 that coal tar sealant was a potent source of pHs and was definitely coming off of parking lots and getting into our waterways. But What we didn't know is once it got into our waterways, what did that mean? Austin is a relatively progressive city. We've got a lot of citizens who are very interested in the environment and in particularly in our water resources. And one of the focuses of our whole group, the 60-odd people who work in the kind of environmental resource monitoring group and management group, is kind of looking at our water resources and how they're affected by environmental pollutants. So our first big question was, yes, it's getting into our waterways, but what does that mean? And we felt like that question really needed to be answered before we could ban coal tar sealant. Kind of to cut to the chase, we did ban coal tar sealant in 2006. And I'm going to talk a little bit about what led up to that ban. But the truth was that we needed to tie that coal tar sealant source of pHs to a bioavailable kind of confirmation that we were seeing degradation in our waterways from that source of pHs. So that's kind of the backstory of this. So yeah, I'm going to talk a little bit about what led up to that, and then I'm going to talk a little bit about how it's been having a ban here for the last 6 years. Let's see. Okay, let's go ahead and jump in here. We are in pretty much the center of Texas. The red dot there on the map, it's the capital. We're kind of dwarfed a little bit by Dallas and Houston around us, but we're a growing city. We've got about 1 million people in the metro area, which expands outside of our jurisdiction, but is all kind of tied to the Austin area. We're an MS4 permittee, phase 1. We have about, as I mentioned, about 60 people in the group that I work in who just work on water quality issues and efforts. We monitor 45 different watersheds in Austin, 3 reservoirs. 2 of those are on the Colorado River, the main water source for our drinking water in Austin. One of them is a power generation coolant reservoir that is outside the city. And just to give you a feel for it, we've been doing this for about 25 years. As I said, the citizens here have asked for a strong kind of environmental city monitoring group, and we've been doing that. So we've got a lot of data about the health and quality of our waters. Okay, Barb went over really, I think, eloquently all the core data that the USGS collected back in the late 90s and early 2000s. And we got to look at this data in around 2001 or 2002 and saw this increasing trend in pHs in our local water body. This is actually in Lady Bird Lake, right? That goes right down the middle of Austin. So this trend was obviously of concern to us. We also, as I mentioned, look at PAHs in all of the watersheds in Austin. This is just to give you a feel. That's kind of what you're looking at there is the overall kind of ETJ or jurisdiction of Austin. And as you can see, those dots represent individual monitoring places where we've collected sediment. We have a predominant kind of problem with pHs in the urban core that kind of goes up and down to the north and south there where you see the red dots. Every one of those red dots is a sediment data point that was over that probable effects concentration that Judy talked about. That value, about 23 milligrams per kilogram, is where you'd expect to see some kind of environmental degradation occurring. So our kind of long-term monitoring data was saying that, yeah, we had some problems with pHs around our city, and we were looking all around, and we also saw some of those yellow dots, which is values that were over the detection limit and maybe of concern, but not up above that PEC. Again, this is just to give context for what we were thinking about at the time. What really concerned us, though, was some of these really high numbers that Barbara Mahler mentioned in her talk. We did have that contaminated sediment grant back in the late 90s, and these numbers worried us enough to start sending them around the country and asking people what was going on with that. And Pete and Barb got involved at that point, and they started telling us that there's no way those numbers could be that high. There must be a problem, as Barbara mentioned. I'm going to talk a lot about this value over here, not a lot, but for a minute, this 161. Some of those really high numbers that you see are in heavily urbanized areas in Austin. That number 161, which is in Barton Creek, right above Barton Springs Pool, was of concern to us because it was in a place where we didn't really understand what the sources were. At the time, there were a lot of different sources of pHs, as both Barbara and Alison and Judy all talked about. But we really were concerned about that, mainly because of the fact that it's right upstream of Barton Springs Pool, a well loved and extremely well appreciated and used resource in Austin, considered kind of the jewel of Austin and kind of the center of the environmental movement in the Austin area. So the fact that we had pretty high pHs upstream of this resource, and in addition to it being a watershed that was relatively undeveloped, led us to do a little bit more kind of deeper source tracking of that particular problem. Again, I'm going to graze through some of this stuff quickly because I know you've heard this story already. But what we found was that if we look downstream of Barton Springs and in Barton Springs, the values of those total TAHs, and again, this is the sum of the 16 EPA priority pollutants that everyone's been talking about today. Those values were less than 5 milligrams per kilogram. As you moved upstream and found to that site above Barton Springs Pool, we started to see an order of magnitude shift there, some values up in the hundreds over a few years of sampling. We found a tributary just upstream of that pool where we jumped up another order of magnitude. Once we got into that tributary, we kept going upstream, so we got up to the head of a parking lot. Up here, another order of magnitude jump. Now we're into the 500 to 5,000 range on that. The y-axis is on a log scale there. Again, obviously we're getting into some serious source issues here. We actually went up to the very top at the parking lot and did scrapings of that parking lot, and that jumped up another full order of magnitude up into the 30,000 milligrams per kilogram range. That was pretty much the aha moment that Tom Bashara, our colleague here, kind of came to at the time that we were learning this. Again, this was all ancient history in a lot of ways. This is back in 2004, I believe, that we started collecting all this data over a range of about 2 years. And this is when we decided, okay, we need to figure out, now we know that this stuff is a source and getting into our tribs and probably causing hotspots all over the city, but is that enough to take it to the next step and try to do something about it? We started talking to the industry in the Austin area and found out that they estimate about 600,000 gallons of coal tar sealant was being applied annually at that time. The wash-off study that Pete and Barb talked about gave us some preliminary data early on that, yes, it is wearing off these parking lots and concentrations much higher than other sources. And we also were seeing the concentrations increasing in our local reservoir and these hotspots all over Austin. But could we, again, tie that directly to actual water quality degradation in our streams and to the kind of the health and ecology of these systems? So that was kind of where we focused our efforts in order to see how far we could take this. We felt like that part of the pie was missing, and it was important. So we set about to do a series of ecological studies that would answer those questions for the Austin area. We looked at it in a weight of evidence approach, where we used that kind of chemical source tracking that you saw already, looking up at sources and tying them to parking lot areas. We also did a laboratory toxicity study where we looked at how spiked sediments would affect lab organisms. We did a field-controlled microcosm study where we put a community of organisms in very controlled environment where we could control the quantity of coal tar sealant inoculated into these little microcosms. And then we did a field verification looking at how parking lots that drain directly to streams might be affecting the communities downstream of those parking lots. So I'm going to quickly go over those 3 studies. The lab tox study, again, there's been a ton of work done in the past on how PAHs are toxic to aquatic life. There's been literature since the 70s on this. But what we really need to do, and this is mainly because of some concerns from the industry and from other folks around the country that said that coal tar sealant, yes, it's got high PAHs, and yes, it's probably coming off these parking lots, but it's not bioavailable. It's so tightly bound to the sediments that this source has been shown in other older studies that it wasn't as bioavailable to biology as some of the other sources of PAHs. So we really wanted to know, okay, so if we spike sediments in the lab-controlled setting and put in kind of typical lab organisms, how will they respond to different concentrations of that coal tar source of PAHs? We spiked 3 different treatments, a low treatment, which is about 17 milligrams per kilogram or below that PEC we've been talking about, a medium concentration, which was about 50 milligrams per kilogram, and a high, which is closer to 300. Those same 3 levels, that low, medium, and high, are the same ones we're going to use in the next experiment. So I just want to reiterate that. What we found, we did that not only with the coal tar sealants, but we also used equivalent weights of asphalt sealants. We didn't want to equivalently try to get the same weight or same pH concentration from the asphalt sealants because it would have been 10 times as much sealant to try to, or 100 times to even get close to that amount of pHs. We just wanted to have a feeling for if the coal tar sealants and the pH and the asphalt sealants in equal masses would affect the biology differently in this experiment. And what we found, as you see in this left bar chart over here, is that our controls had 100% survival. The organism we're talking about here is Hyloas teca, a little crustacean. The controls had both 100% survivability or survival. The low treatment in the coal tar had a significant loss of mortality of the organisms at 81. The medium dropped way down to 30% survival, and then the high was down to 13. The asphalt sealant showed no significant toxicity to those treatments. But again, you got a nice dose response of these organisms to the coal tar sealant. And these numbers, again, that first one is below the PEC, and the second one is quite above the PEC. Now, if you add UV light to pHs, this is another kind of known phenomenon in the literature that UV light will enhance the toxicity of PAHs. So we followed up after that first 28-day exposure period and added UV light. And what that did is actually make the toxicity in both of our treatments, both the asphalt and the coal tar sealants, significantly more toxic. We lost all the almost all the organisms in the low treatment, going from 81 down to 10% survival. And then in the medium and the high, we had no survival in those treatments from the coal tar sealants. And another interesting thing is that we actually did get a dose response toxicity response to the asphalt sealant after that UV light was added. So that's what we got. We felt very confident that our results were consistent and pretty clear that we had toxicity to coal tar sealants at levels that would be predicted by that PEC, that probable effects concentration. All right, the next experiment, as I mentioned, this was trying to get at more of a community or an actual real, more of a field effect, but in a more controlled setting. And what we did is we spiked actual little tubs of sediment that had been inoculated with the same levels of low, medium, and high concentrations of PAHs from coal tar sealants using that ground-up pavement sealant. Oh, by the way, that ground-up pavement sealant is made by taking sealant. Tom Bashara, our colleague, also came up with this method of painting sealant, coal tar sealant onto clean glass, and then waiting for 3 days for it to dry, and then scraping it off that glass so we could have a kind of a dried product for use in these experiments. What we found in this experiment, let me make sure I got that right. So we inoculated these bins with different levels of coal tar sealant, having both, and then we put in a community of organisms collected from a reference stream into these bins and waited for 24 days, and then pulled them out and looked to see how that community of organisms responded to those 3 different treatment levels and compare that to a control. What we found was this general pattern in many of the measures that we looked at. Kind of the most typical was what you're seeing here as number of organisms that we found in these bins after the exposure period. So that left axis is actually a total number of organisms. What we found was kind of an enhancement of the community in the low treatment, which is kind of odd, and I can talk a little bit about that. But in the medium and in the high treatments, we saw significant dose responses to basically to that PAH coal tar sealant source. An interesting thing to note on there, we used another measure besides the PEC, that probable effects concentration of 23. We also used the equilibrium partitioning sediment benchmarks, or the ESB toxicity units that the EPA developed to look at how toxic these PAHs are in actual in sediment settings. So they basically kind of standardize it based on the different pHs that are there and the amount of organic carbon that's in the sample to tell you how toxic sediments might be to actual organisms. And what you see in those numbers there is that the low treatment actually was below that toxicity unit of 1.0. Once it's below, when it's above a 1.0, it's considered to have significant toxicity expected in these communities. So what we're imagining is that this was not high enough to actually cause any toxic effects, and possibly was due to an actual addition of carbon sources and kind of a ramping up of the microbial community in this kind of a confined environment. But what we did find is once those toxicity units went above 1, we started to see toxicity in the entire community in the medium and high treatments. If you looked at actual individual responses in these microcosms, we saw even a little bit more of a pronounced and clear dose response. This is a Procladius midge that is often used again in kind of environmental monitoring. It is, we found that it had a very clear and significant dose response to these coal tar sealant treatments, dropping in organisms as the concentration of sealant and pHs in these microcosms increased, going down to actually no survival in the high treatment over here. All right, and then our final experiment, this field study, this is, again, more of a confirmation of what we'd already kind of documented in the lab setting. What we went out and did was we found parking lots that drained directly to a stream. In other words, there was a direct connection of some sort that went from a parking lot that was confirmed to be sealed with coal tar sealant that drained down into the parking lot. And we looked at the sediment concentrations of pHs above that parking lot drainage and below that drainage. We looked at 7 different parking lots, and 5 of them we found had significant increases in total PAHs below that parking lot entrance. In some cases, well above, from non-detect down at the bottom here all the way up to 33 or 34 milligrams per kilogram in this first one. Some of the other ones were much smaller in their increase, but all of them had notable increases in pH concentration below those parking lots. Then what we did is we looked at the communities above that parking lot and downstream of that parking lot in riffles and pools. And generally what we found was there was a definite decrease in community health downstream of these parking lots in all 5 of these cases. The general pattern is expressed over here in this right graph, where you're looking at loss of taxa or loss of diversity on the y-axis, and then a change in those toxicity units. In other words, as it goes from the upstream, we looked at the toxicity units upstream versus how negatively they were affected by the change in pHs at the downstream site. And we found that that change in toxicity very well correlated and explained the loss of taxa that we were seeing at these sites. On the R-squared on that one, it's about a 0.75, which is pretty good for a small data set like this. So again, we're seeing increases in pHs downstream of parking lots and a predictable community response to those increases. So at this point, as I mentioned and kind of reviewed before, we knew that the coal tar sealants were a concentrated source. We knew that they were possibly a major source to the pHs that, to the streams that were studied in Barbara Mahler and Ph.D. Metre study, and that we co-authored with them. And we also were able to demonstrate clear ecological impacts in Austin in our local stream systems. We used chemical tracing, we looked at lab and field toxicity, and we did field verification. At that point, we were ready to go forward with a ban on the use and sale of coal tar sealants in Austin. Again, this is in about 2005 that we really came to this conclusion. We started an intensive ban outreach effort. We had several stakeholder meetings. We did presentations of a lot of the biological data that you just saw and some of the other chemical tracing. We published several of these studies in peer-reviewed journals. We did technical briefings around the country to EPA, USGS, and the Department of the Interior. And we also even did a congressional briefing in Washington, D.C. It was very exciting for us, down Texans. And then we also did an intensive public process here in Austin that is required to go through any sort of an ordinance adoption, which entailed going through several public board and commission meetings and then eventually taking it to council, where it was voted in unanimously by our council and supported. So at that point, which was in late 2005, we had a ban in Austin, Texas. What that looked like was prohibiting the use in our jurisdiction and the sale unless that intended application could be documented to be outside of our jurisdiction. This is essentially hasn't happened. No one is selling coal tar sealant in Austin, so this really hasn't been an issue that we know of. Enforcement has been a kind of a long and pretty relatively simple process for us because we've incorporated into our existing programs It's mostly driven by complaints. If people see someone sealing and they're concerned about it, we have a hotline, and our staff spend a lot of time out and about in the city, and they have gotten really good at noting when sealing is going down, and they've got some really good field tests for documenting when it is or isn't coal tar. The fines, if someone is caught and confirmed, it can be up to $2,000 a day, although we have actually never had to fine anyone. We've had 9 violations to date. Those violations have been kind of across the board in different size lots and in different locations around the city, but in general, they're kind of outside contractors that have come into Austin and not claiming ignorance that they didn't know the local laws. That's kind of the generalization. In general, the way we've dealt with those is kind of deferred adjudication, which means we establish a period in which we're going to work out a solution together, and we've always been able to work something out during that. It's usually a 6-month period. Almost all of those have been in some kind of remediation. That looks like often, in most cases, it's laying over a surface coating of an alternative sealant product that's not coal tar, and almost all the time that's been an asphalt-based product, kind of an encapsulation of the seal coat that was put down. In one case, they actually removed it using a kind of a shot blast approach and a vacuum. In one case, they actually encapsulated the entire sealant with a new coating of asphalt. In addition to our kind of enforcement, we did have one big state legal challenge. A big industry player here in Texas took this to the state environmental agency, the Texas Commission on Environmental Quality, and basically asked that they not allow the city of Austin to ban coal tar sealants because it was against some obscure state rules, and also that they didn't have sufficient technical and scientific proof that this was the problem. We went and did a big kind of briefing and kind of a quasi-legal hearing at the Commission on Environmental Quality, and won that, where the state sided with the city and said that we had perfectly legal rights to have an ordinance like this, and we provided sufficient scientific evidence to uphold our ordinance. So that was really a breath of fresh air for us. We have, as other folks have mentioned, we feel like right after we put our ban into place, locally, Lowe's and Home Depot both started pulling coal tar sealant off their shelves. And pretty soon after that, I think it was about a year later, they decided to do that nationally. Again, I think it was based on what Judy said, that there's a very common and relatively comparably economically costing alternative with the asphalt sealant, so that wasn't a big problem for them. There's also been a lot of other post-ban research and media attention that's kind of come up here and there over the last 6 years. Anything from different papers that Pete and Barb and other folks in the area have published, other agencies and states that have kind of read about what we did and decided they wanted to ban something too, and we've often gotten involved and provided them with technical help on what they were working on. Just recently, the Austin Independent School District decided that they were going to basically remove all the legacy coal tar sealant that had been put down before our ban went into place over the next 3 to 6 years in an effort to eliminate that source from our local school system, which we're very happy about that. And another kind of great development, our House Representative Lloyd Doggett recently put together a bill, and that's on the House floor right now in committee actually, that would ban coal tar sealants nationally. Not sure how much kind of momentum this bill has, but we're hoping that if not this year, maybe next year, it'll come back and have a little bit more. A couple other things I kind of wanted to talk about, things that came up in other questions from the previous talks, are the idea of alternative products. For a while, we would actually list all the alternative products that we knew on our website, and we still keep that up to date. But it's essentially mostly asphalt-based products. There are a few other latex products that we've been introduced to and heard of, but we really don't see them used in the Austin area on any kind of large scale. I think there's been a couple applications around the city. So as far as the the hope of new products that could, one, not be black or be gray or some other kind of color that wouldn't be such a heat island issue and wouldn't absorb as much heat, and also that would maybe stay longer, or it would not have any kind of pHs or other chemicals in them. We haven't really seen that market develop here. Disposal issues, people asked about that. In Texas, at least, it is the landfills that we work with. It's legal in Texas to basically take coal tar sealant and sealant contaminated soil and put it into our landfill. So that hasn't been a huge issue for us when we have had to do remediation or deal with contaminated soils. But I understand that in other parts of the country that may be a lot bigger deal. Another thing I wanted to point out is that although the industry out there is unhappy a lot of times with what's going on with moving this away from coal tar sealants and toward asphalt, they are generally, from what we understand, they like using coal tar sealant, a lot of them at least. And what we found is that even if there's alternatives available, the industry tells the customers that the coal tar sealant is really what that is going to stay longer and be a better product. So we found that they end up using them almost exclusively when those are an option. I'm going to quickly go through kind of some band monitoring that we've been doing over the last, since well before our ban went into effect. Actually, as I mentioned, we've been looking at pHs in Austin. But once our ban into effect, we really wanted to know whether our ban would reduce the kind of the pH problem around Austin. It's only been 6 years, and as I think Barbara Mahler kind of stated pretty clearly, these are very stable and long-lived compounds. They're going to be out in the environment for a long time. And also, we believe, and we still see them out there, there's a lot of legacy sources in Austin still that are still shedding some quantity of sealant from those aging lots. So we're still getting influxes probably. So we think it's still too early to make any kind of strong conclusions about how well this ban is working on reducing pH loads to Austin's water sources. We also have noted recently, we looked at some of the character of the pHs that we're seeing in our water bodies, and a lot of them are those larger, more benzene-ringed, heavier pHs, and kind of generally suggesting that they're older in character. So we're thinking that falls into our assumption or our hypothesis that these are legacy sources. We're also seeing in some watersheds that those patterns are actually, the trends over time are decreasing. There's 3 or 4 that we've seen that, a very distinct decrease. But most of our watersheds are not showing any clear spatial pattern, or excuse me, temporal pattern, and no strong or even, and in some cases there are actually some increases, and we're still looking into those. This graph that you're seeing here is our receiving water body, Lady Bird Lake, that kind of gets drainage from a lot of our urban creeks. And this is kind of where we want to look for long-term trends. We're really not seeing anything, as you can see, over the last 5 years since the ban was put into effect. Pretty flat. Maybe at the end here we're maybe starting to see a decrease, but who knows? It's going to be at least 10, if not 20 years before we're going to really be able to tell how much of an effect this ban has had on long-term PAH trends. All right, that's pretty much what I got. I guess one thing I did want to point out is that, as I mentioned early on, Austin is a relatively progressive city. I think a municipal ban is a very inherently a political process, and it can be very painful in a lot of ways, and we've seen that throughout the country when other municipalities have tried to do this. I think that it's questionable how effective or how feasible it would be for cities all over the country to institute these bans. I do think the evidence and the science is growing quickly and very kind of convincingly, but I think it's really difficult to think that everyone can go through the same process. I think that we got lucky and stumbled upon this, and again, in a progressive environment, we're able to make this work, and I think we did a really good thing. I guess I'd just like to open it up to questions there.
Thank you, Mateo. We'll now open the floor to questions. You can type them in. I have a few ready to go right now. First, what is the purpose of using UV light for the bioassay test?
Okay, so UV light has been shown in a lot of the older literature to excite or enhance the toxic effects of PAHs in aquatic environments in the sediments. The exact mechanism, I'm not completely sure, but it's a narcosis effect, and what it does is it increases the cellular ability to handle the kind of the toxic effect that those pHs have on membranes. Is that enough?
Yes, thank you. Our next question, and by far the most popular, is there a field test for determining coal tar seal coat versus asphalt?
Yes, there is. We actually have a write-up of it, and we're gonna be putting together a little kind of official report on how to do that test and kind of an overview of how we've used it here in Austin that I can send out to folks if you guys want to email me. Chris, I think you're going to put our contact information out there for everyone, right?
Yes.
Essentially, you scrape a little bit of the material off of a parking lot, and you have to do that carefully because there can be layers and layers of sealant on a parking lot, so you can't just scrape everything. You've got to try to get the layer that you really want to focus on, and you dissolve that in a solvent. And basically, the solvent that we used, if it's an asphalt sealant, it dissolves into the solvent and makes a black muck, coffee-looking stuff. And if it's a coal tar sealant, it does not dissolve, but it turns the solvent into kind of a tea color or a kind of what is the word I'm looking for? Like a tannic color, basically, and it sometimes kind of glows a yellow color.
Okay. Next question. What sort of outreach have you done to raise awareness of the ban?
In the Austin area?
Yes, I presume.
Okay. Well, we've done quite a bit. We did a lot when the ban first went into effect, obviously. Actually, before the ban went into effect, we did a big outreach campaign calling for a voluntary ban. We contacted all of the applicators and manufacturers in the Austin area, let them know what we're doing, and brought them together for those stakeholder meetings that I mentioned, sent out flyers to everyone, letting them know that we were concerned about it and that we wanted them to voluntarily stop using it. Then once the actual legal ban went into effect, we did that all over again, sent out flyers, working with both the applicator community, the manufacturers, and also to retail businesses around the city that sold and or had sealant products on their shelves. And then we've continued that process. I think almost annually we're in contact with all the retail folks who sell and apply sealants in the Austin area, kind of letting them know what we're doing and what's going on and what concerns are around.
Next question. How long after coal tar seal coat is applied does it remain a source of PAHs? Is there a point at which remediation is no longer necessary because all the PAHs have already been released to the environment?
That's a great question. You saw a lot of the graphs that we've seen today, particularly Alison showed some of those stormwater graphs showing that kind of basically a loss of PAH load over time. Yes, I think at some point it would not be worth a whole lot of trouble if 80, 90, 100% of the sealant is worn off the parking lot. I think that curve and that rate is highly dependent on a really wide variety of things: climate, how well it was applied in the first place, the actual type of product that's put down, the skill that the applicator had. We did a wear-off study published in Environmental Science and Technology and looked at a bunch of lots around Austin and kind of the wear-off rates that we saw there. And basically after 5 years, most of these lots had lost anywhere from 15 to 50% of their sealant. So where that kind of end of that trail is, where you really don't have any sealant left, I think is highly variable. But I do think after 5 to 10 years, you're probably looking at limited diminishing returns on spending any effort to clean that up.
Next question. Are you aware of the occupational exposures to workers who apply or remove coal tar seal coat?
I'm aware that it's a hazard. I don't actually know a lot about the OSHA rules, but from what I understand, there's quite a bit of regulatory input in this field. I don't know we hear a lot from the industry that they don't have any problems with occupational health issues with the sealant, people who actually seal at coal tar sealant. But I think it seems to me that if you're spending all your time with that stuff volatilizing and in the air while you're spraying, it seems like it would be an occupational hazard for sure.
Next question. How have coal tar seal coat producers and suppliers been impacted by the ban, and how did Austin address impacts to businesses?
That's another really good question. Part of our outreach and part of our continuing kind of work with the industry here in Austin is understanding how economically, that was one of our big concerns when we started talking about the ban, was how is this economically going to affect small businesses and even larger businesses in the Austin area. From what we could tell talking to them and talking to other applicators around the country, the fact that there is an alternative product, the asphalt-based sealant, and that it is readily available and uses the same, essentially the same technology to apply it, not exactly the same. We believe that there was a kind of a one-to-one trade-off there, and we believe that there was minimal economic damage done. Most of the companies in the Austin area just switched over to asphalt-based sealants. I'm sure that there was some problems with different success rates that people had with the different products, and I'm sure that there were some folks who decided they didn't want to seal at all if they couldn't get coal tar sealant, but we haven't been able to quantify any of that. Our general feeling is that the economic effects on the industry as a whole were pretty minimal, but we don't have any real direct way of measuring exactly how that played out over the last 6 years.
Next question. Is coal tar seal coat more effective or longer lasting than other sealant types?
Yeah, boy. I don't have an answer to that question. As kind of Pete Van Metre said, there's been a lot of questions about that over the entire time we've been looking at this issue. The industry has not documented anything in the peer-reviewed literature that we can really sink our teeth into as far as which ones work better. There is some evidence in some of the kind of the ASTM or standard testing methods that coal tar sealants is potentially lasting longer, definitely under kind of a gas or oil kind of contamination scenario. And there's also, I would call it anecdotal evidence from the industry that coal tar sealant holds up a lot better and a lot longer than the asphalt sealant products. Our kind of anecdotal and field experience here in Austin is that there are definitely a wide range of quality in the asphalt-based products, and some of them really don't seem to hold up very well, and some of them seem to hold up really, really well. But we don't know overall if there's any kind of clear answer on that, other than that one of them is a lot more toxic and problematic from an environmental perspective. So whatever other issues there may be for the asphalt, we feel that they're probably small compared to the environmental costs.
Next question. Are these sealants a coal tar epoxy? That would be a two-part system that is mixed prior to application?
No. It's an emulsion. Again, I'm not an industry expert. There's a lot of people around who know a lot more about this than I do. But the way that they make coal tar sealant is they emulsify actual refined coal tar with water, sand, and clay particles. In this, I think it's a pretty specialized process where they kind of mix it all together and it all gets held in an emulsion, and then that emulsion is sprayed on the ground and then it dries in place. There's not any binder or epoxy kind of process from what I understand. Asphalt sealant's a little different, but I think it's essentially the same idea. You take the binder, in that case, is your asphalt sealant instead of the coal tar, and it's also put into a slurry and dried on site. But it is affected a lot more by temperature than the coal tar sealant is.
Okay, that was our last question. Thank you, Mateo.
All right, thank you all. Again, I welcome any questions from cities around the country that are interested in this topic. I had to skip over a lot of stuff, and we do have a lot of people, a lot of them are in the room right now, who have been working with this issue for the last 10 years, and I think anyone who wants to send us any questions or concerns, we'd love to hear from you.
Thank you, Mateo. This concludes today's webinar. Thanks to all of our speakers. As a reminder, if you have any questions that were not addressed in today's webinar, please contact the speaker or EPA at the address on your screen. I also want to remind you to fill out the webinar evaluation survey that will soon appear in your screen window. Please consider completing the survey and let us know your thoughts. We do appreciate your feedback as we work to improve our webinars. EPA is planning to hold additional stormwater pollution prevention webinars in the coming months, so we are particularly interested in your feedback on what other topics you would like to hear about. And I'll leave the screen up for a second before going to the next certificate slide so you can take down this contact information. Please don't forget to download the certificate for participating in today's webinar. You can type the link that appears on this slide in your browser's address bar to access the PDF file of the certificate, or you can type in your name and print a copy for everyone attending. You will also receive an email with a link to the certificate in about 1 hour. Thank you for your participation, and we hope that you will join us in future EPA stormwater pollution prevention webinars.